Just enter? Oh, the arrow key. Okay, got it. Well, maybe a clicker, actually. You have one? Well, good morning. I mean, it's about time to start. My name is Benoit Dewan, for those of you who don't know me, and I am one of the 3 conference co-chairs, and the other 2 are, can you see them? Yeah, the other 2 are Dr. Ipek Uz, colleague of mine, as well as Bennett Landman, who is a colleague and also my boss. I mean, he's the chair of the Department of Electrical and Computer Engineering. So on behalf of Ipek, Bennett, and myself, a very warm welcome, and actually a beautiful day in Nashville today. You know, it can be hot and steamy sometimes. Today is really perfect. So I hope that you are all settled, and that you're ready for an exciting scientific program, for fruitful discussions, for meeting new and old friends, and also for learning more about both our institution and Nashville itself. So it's just an opportunity to visit the city a little bit. Now, if the weather permits, and I think it will do, I would strongly suggest you to take a stroll in the campus. I mean, the campus is also an arboretum with more than 6,000 trees. So that's something that is really worth looking into. I will also, make you appreciate, and I think that's important for a community, it will make you appreciate how close the university and the medical centers are located. So, which is, of course, is a very strong asset for the type of research and activities that we all do. Now, before we start our scientific program, I would like to introduce Dr. Sibel Raver. She is, who has graciously agreed to talk to us this morning. Now, Dr. Raver serves as the Provost and Vice Chancellor for Academic Affairs. She is an internationally recognized developmental psychologist whose leadership has spanned research, clinical, academic, and administrative settings. She is a fellow of the American Association for the Advancement of Science and also the Cornelius Vanderbilt Professor of Psychology and Human Development at Peabody College, which is our College of Education. Though she has held faculty positions at the University of Chicago and Cornell University, and she was the Deputy Provost at New York University. At Vanderbilt, she oversees all faculty, staff, programs, and initiatives for Vanderbilt's 10 schools and colleges. In other words, we all work for her. Since joining Vanderbilt in 2021, she has catapulted the university's scholarship and research reputation forward by recruiting visionary leaders, launching new pathways for faculty and student support, and establishing processes to facilitate bold and collaborative discovery across the university. Now, one initiative our office has launched, and we are all here benefit from, is the Sesquicentennial Grant Award, which was created to support activities and projects that engage with the university history, look ahead to its future, and explore what makes Vanderbilt distinctive and unique. Now, the organizing team received one of those awards, and in addition to providing funds to defray some of the cost of the organization of this event, and which helped us to keep it at a reasonable level, it expanded my vocabulary. For those of you who are wondering, the sesqui appears to come from the Latin word semi. Semi means a half, and the contraction of semi and qui means and. So sesqui would mean 1.5. And that's sesquicentennial, means that Vanderbilt is 150 years old. So that's where it's coming from. Took me a little bit of time before I understood where it was coming from and where it was coming from. I didn't know the word, you know, not being a native language English speaker, don't know, my vocabulary is limited, but that was an interesting thing. So not only did it broaden my vocabulary, but also it helped us to organize this event. Here for that, we thank you, Sibel, for this initiative, and also for taking the time this morning to share her vision for Vanderbilt. So, Sibel.
Good morning, everyone. It is such a pleasure to be here to welcome you all. No problem. There we go. Now you get to see the sesqui and the sen. It's just great to have a chance to welcome you to Vanderbilt, to welcome you to Nashville. For those of you who are our Vanderbilt students and our faculty, it's wonderful to have you here as well. I really want to thank Benoit and Bennett Landman and Ipek Ogus, as well as other faculty who have organized this event and this meeting. From my perspective, it is absolutely central that you have a chance to connect with each other, with industry, and with the nation's leading scholars, or actually the world's leading scholars, from disciplines that are not your own, that we find that the best ways that we can discover new knowledge and new solutions is often in interdisciplinary discussion and interdisciplinary convening. So I'm very, very excited to see this interdisciplinary convening of computer scientists, machine learning experts, and neuroscientists, for example, as I was just seeing in the wonderful poster session. We're particularly also deeply interested in and connected to and leading in the fields of healthcare and artificial intelligence. If you're interested in that topic, you have come to the right place. In that, machine learning, I think, holds tremendous potential to not only revolutionize what we know about the brain or about what we know about detection of disease, but also how we think about medical practice and healthcare delivery. So this opportunity to have that conversation at the interstices of those different fields is incredibly important. You are actually pushing the boundaries of what is possible in the field of medical imaging, using machine learning algorithms to analyze vast amounts of medical data. I was just saying to Benoit that I was trained essentially pre-functional and structural MRI in brain science, and was really using more physiological and neuroendocrine assays. And it's just amazing to see how fast that field is moving in just one area of specialization. But we could think about so many other areas of medical imaging where it has been really quite shocking and exciting to see the speed with which the field is being revolutionized. So at this nexus, at the forefront of this exciting and important field, I'm particularly excited to see what you are all bringing to the table and learning from each other at this cutting edge. One of the reasons that we made this investment in this kind of event, in this kind of meeting, is because of the very big push at Vanderbilt for the theme of discovery as the driving value, the driving mission of our institution. I think many universities are known for really being able to pass forward a canonical knowledge, and it is really only those best universities that are known for creating new knowledge from the undergraduate level all the way through the senior faculty level. And that really happens here, again, through a tremendous partnership between Vanderbilt Medical Center and Vanderbilt University. It is really important for you to know that we're moving very quickly in an upward and fast-moving trajectory in our position in terms of medical research and university-related research. Under Discovery Vanderbilt, an initiative that we just launched, that I launched in October, we essentially decided to be very clear about our objective, which is to be extremely well-known as well as high impact in our research. So, for example, we recently achieved the $1 billion mark in research expenditure, which is just a brute proxy of how active our research is at Vanderbilt, surpassing actually MIT and being in the top 10 of private universities in the country in terms of our research effort. So we want you to come back to Vanderbilt to think about the next stage of your career. If you're here now as a visitor, we want you to walk around campus and meet each other and meet other faculty and other students, knowing that this is a place where so much incredibly great work is happening. In that regard, we really want to be clear that we pass that forward in a deeply collaborative spirit. So we think of ourselves as cutting edge, but not cutthroat, very much focused on mentoring and supporting the next generation of investigators as you all carry this incredibly important work into the next decades and century. An example of that kind of mentorship is seen among our faculty. I think a lot about Katie Chang, an assistant professor and researcher in our School of Engineering, who's leveraging the power of computational analysis and machine learning to really think about a wide range of illnesses, from depressions to Parkinson's disease, for example. I have recently seen her undergraduate research assistants not only starting a podcast on the work that they do, but winning awards on federal, national levels for their young investigator status. I can think often about other scholars who are in similar areas doing tremendous amounts of work, not only obviously Professors DeWant and Eric Takasik, but other faculty who are being supported by the National Institutes of Health developing artificial intelligence algorithms. Dr. DeWant's work on monkeypox lesions, for example, is just incredibly important and extraordinarily timely as we face that rising concern in terms of the threat that Dr. DeWant and his colleagues were so on the forefront of addressing. In that regard, the power of machine learning can really truly be realized through collaboration between engineers and physicians, and between the university sector, the public sector, and the private sector. It was wonderful to see, for example, that there is a number of private corporate partners who are represented in the poster session. So again, let me thank Bennett Landman, Kurt Schilling, and others whose work is not only changing the way that we can think about machine learning and medical imaging, but also for the work that you do at the university leadership level, really being able to carry that intersectional and interstitial work to the forefront, not only at this university, but for the world at large. Thank you, everyone, and have a great time here. Enjoy your visit, and please come back.
Thank you, Sibel. Well, clearly, organizing an event such as these ones take, you know, a little bit more than a village, kind of a small city. And we will not be able to thank everybody at this time, but they will be thanked as along the conference as things go on. Now, not only it requires a village, but it also requires a village chief who keeps everybody rowing in the same direction and keeping them on task. And I do not think that my colleague and as I said, boss as well, Dr. Landman needs a lot of scientific introduction in our community, but he has been, without his leadership and his direct involvement in all aspects of the organization, almost all aspects of the organization, because the technical content of the conference was the work of Dr. Uz. Said without the direct involvement of Dr. Landman, this event would not have occurred. I mean, actually, I think that many of you have received emails, numerous emails, at all days, all hours of day and night, and sometimes one gets a question, is ready to answer that question, and it's already answered, too late. No, Bennett has responded quicker than everybody else. So, Bennett, thank you very much for leading this, and I will let you give us some information about the logistics of the event.
Thank you, Benoit. I'm sure you're ready to all block my emails. It's okay. Today, we're in Nashville. This is just the start of MIDL. I was looking back, and just before the pandemic in Amsterdam, then London, Montreal, Ludwig, Zurich, and here. It's fantastic to bring this community, as Provost Raver was saying. We hope you come back. And it's really special to be able to share so many aspects of our campus, our lives, our sort of way of being with you. And we've set up a lot of space to make this happen in animation, MIDL 2023. So you've seen where we are here. We're coming from 267 current registrations, over 30 countries and 5 continents. So a big portion of the world is coming, and it's fantastic. We're very thankful for our sponsors, especially, as Benoit mentioned, the Sequicentennial grant that allowed us to sort of kick this off and get it going, as well as VICE, our Institute for Surgery and Engineering, of which Benoit is the director, our Vanderbilt University Institute of Image Science, and I see a number of people here affiliated with VAAS, led by John Gore, which is just sort of our partner institute in the Med Center side. We are offering tours. So if you'd like to come sort of meet researchers in their natural habitat, and you're all researchers, so you sort of know where we live, but if you'd like to kick the tires and see our cool space and play with the robots and 3D printers and that kind of thing, come on by. There's a QR code up here. There's a QR code at the front desk. We'll make it happen. Now, this also really couldn't have happened without some fantastic sponsors that have been with MIDL since pretty much the beginning for most of them, and have invested in the board, have invested in this idea of having a small conference where we have space around the poster boards. We have time to talk. We have time to break down. You have breakfast, you have lunch, you have dinner, you have all of the ad hoc conversations, and there are few enough people in this room that I challenge you, I think you can probably meet everybody. You know, go for it. Make it happen. So a little bit of logistics now, because that was promised. We're in the Student Life Center. We're standing right here directly in the middle. That's me on the stage. Most important, 100%, that's where the coffee is. It's being refreshed every 2 hours. There should be lots. There's snacks there as well. There's orange juice, decaf, water. The blue one is the clear coffee, danger. But it's there if you'd like it. Now, once we've had the coffee, second most important, the restrooms are there, right around the corner, and there's more downstairs. So the way to get to the breakfasts and the lunches, you can either walk way around on a campus tour of this way, seeing all of our trees. Great. If you'd like the shortcut, straight out this building, it is less than 0.2 miles from where I'm standing into the cafeteria. So it's right there. This is our corner of campus. We recommend zipping out the back door. There's 3 signs, and you're right in the dining. And you can zip back here. The buses all will meet at the Star, which is immediately out here. And there's a little round area, a very large red steel statue. And then if you came yesterday or staying for Thursday, which would be wonderful, Benoit and I live in this building, which is Featheringill, which is basically exactly out the front to make a triangle to Rand. Now, new this year, we're trying something different. We're sort of following what ISMRM and other people have been doing for power pitches and teasers. I think we're calling them teasers here. So after several oral sessions, we're going to have people who are presenting posters in the future and the next day line up here and give a very brief description of a slide or so about what they're doing. It should be fun. If you hate it, let us know. We'll tell the next people not to do it. If you like it, let us know, and we'll make it happen. It's going to be easier to navigate where everything is, because posters 1 through 30 are in there, posters 31 through 60 are in there, and every day we have a different set of posters. There's a Monday and a Tuesday and a Wednesday set of posters. So every day there's different posters. Key thing, if your poster location, M30 is even, M29 is odd, the 9s, 1, 3, 5, 7, 9, are in the morning, 2, 4, 6, 8, 0 are in the afternoon. Please have at least one poster author there discussing, because that's sort of the whole point, to be able to talk about the science. We have a lot of space around the posters. It shouldn't be crowded. It should be pleasant. And there's refreshments at all of the poster sessions as well. Please leave them up the whole day, even if you're only presenting in the morning. And if you're presenting in the afternoon, please come in the beginning and get them up. It just makes for a better experience for everybody. If you have any questions or your poster got moved, I probably did it because you put your poster number up on your paper number instead of your location number. It's okay, man. I can move push pins. If you can't find anything, we'll make it great. Let me know. Now, our colleagues up in the Northeast had a little snafu. We want to look at 54% out of LaGuardia of whoopsies. And unfortunately, their favorite destination to cancel was Nashville. Sort of the top destination canceled from the Northeast was us. So we're doing a little bit of an audible in terms of people who can't show up. So you'll see poster numbers shifting on the program site. Your number won't change, but other people's numbers who couldn't get here because of a flight might shift from a Monday to a Tuesday to make space. So if your poster that isn't here today, look on it. Dr. Ooze is blinding me in the light. There, waving, yes. It has been valiantly making sure that everyone has a time to talk. So if you don't see a poster here today, check again in a couple hours of what the number still is, and it will likely be later this week. In terms of that, we've had one thing that we couldn't easily switch. There is one person trapped in New York waiting on standby who has a talk at 2 p.m. today. If anyone would like to switch from an oral session later this week to today, there will be eternal gratitude. Otherwise, we have a plan B, which will be fun. It'll be scientific, but eternal gratitude if anyone would talk to Professor Ooze and, right there, yay, switch to today. And we'll update all the programs and everything else so all the proceedings make sense, and the live streams are online. Again, new this year, we've built in some collaboration spaces so that if you want to sit down and go deeper into ideas, great. So in the back of the Board of Trust room, we have 4 large rounds set up with tables to work, talk, grab a coffee, use them, they're yours. Additionally, downstairs, which is downstairs and there, there's also an elevator that goes down 1 floor. There are 2 collaboration spaces. One, if you really want to practice your talk, or even just show somebody else a talk that you have, we have a small little room here called Meeting Room 3. It seats about 15, and you're welcome to use that for presentations, discussions, that kind of thing. And immediately next to it, we have a larger rooms, except for tomorrow at lunch where we're having the middle board meeting. It's also open for collaborations and discussion, and if you want to live stream us, you're welcome to. We are live streaming, thank you. Downstairs, you can do that too. It's all good. Lunch, most important, we are seeking to avoid a rush that happens at a lot of conferences where we all say, leave, and 500 people go line up, and then you wait an hour for lunch. So we have the entire hour, noon to 1, as our dedicated area in Rand. We're supposed to be the people there. If people go a little earlier or a little later and miss some of our sessions, it's okay. To provide randomness, we've randomly printed on your badges either a drum or a guitar. I'm a drum, so it's 12:30. It's a suggestion. You can go then and meet new people, or you can go at a different time and meet old people, or you can go in between. The whole thing is just, it's not that your food won't be there, it's just to, make it lower key. We'll be leading a walk over at noon and 12:30 with some of our fantastic volunteers if people want some directions there. But again, we've put up yard signs and hopefully it'll be super easy. If there's any problems, please let me know. Tonight, we have a welcome reception at the National Museum of African American Music. So the grand atrium will be serving past hors d'oeuvres and bowl stations and drink tickets and alcoholic drinks and unlimited non-alcoholic drinks sort of in the basement there. We'll meet around here about 6, buses starting to leave 6:15 or so from, again, the area. Those will run on loop, and there'll be a reception until about 9 or 9:30 or so. The key thing here is you'll need your middle badge. There's a lot of people downtown, and if people see free booze downtown, we could have a lot more than 200 people in the museum very quickly. So if you want to get in the museum, middle badge. Once in there, also keep doing it just to avoid it turning into a Nashville party. If you'd like to do a Nashville party, take off your badge, go outside, do whatever you want outside of the middle conference. The buses will loop back from 10 o'clock, starting from when people want to leave about 8, coming until 10. Now, what did I just say? Last bus 10. We're not counting who's going or who's coming. You're adults, and if you want to stay and take an Uber home or a Lyft home or something else, great. But last bus, 10 o'clock, and have fun, but last bus, 10 o'clock. Tomorrow, we're going to the Parthenon. So Nashville actually has a full-size, intact sandstone replica of the Greek Parthenon built in our Centennial Park, which is the 100th year anniversary of Nashville. Right across the way, it's about a 10-minute walk or a 15-minute saunter. We'll meet here about 6 o'clock and then have volunteers lead a slow walk over there. If you don't want to walk, we have a bus looping. It's not the big buses, it's just one of the smaller 25-passenger shuttles, and it will loop if you want to. There'll be enough space. If everyone wants to take the bus, it's fine, but it's supposed to be a really nice night. For that, you will need, again, your middle card. And then on the back, you have a little meal card, a menu card of which you would like. If you want to change, see me at the front desk because I had what you had. I've been asking everyone to make sure they're happy. If not, great, it'll be wonderful. It's a short walk back, but again, the last sort of small bus shuttle will come back about 10 o'clock, at 10 o'clock. So if you have any questions, let me know. It's literally a 2-minute Uber ride back here if you'd like, but last bus 10. We're also trying something new to engage online participants rather than setting up monitors and trying to have a hybrid thing all of the time, which at least for me becomes sort of a cognitive overload. We are putting the online participation in a 1-hour time slot in the morning, which then makes it sort of reasonable for both Asia and Europe, which are optimal time zones. Dr. Huo is in the room somewhere, not waving his hand. Dr. Uz is pointing at Dr. Huo. Way over there. Okay, great. He'll be running a gather town on Wednesday morning for everyone who couldn't come for our various lovely international policy discussion problems. And also people who wanted to have a sort of virtual presence of their online areas. Join remotely, join here. The streaming should be pretty good and it'll be fun. On Thursday, we have the Vanderbilt NVIDIA Monai meetup. A number of hybrid speakers will be in Featheringgill walking us through the Monai system, providing tutorials of how you can release your tools in ways that millions of people can use, or learning how to do sort of the tasks in other fields that may be relevant for what you're doing. It should be a lot of fun. Breakfast will again be at Rand on Thursday, and we will have a local food truck at Featheringgill for lunch. I'd like to thank everyone who came to make the Vanderbilt Electoral Symposium such a success, especially Ji Ying and Katie Chang. Again, I'm blinded, if it can point at them. And thank you so much for making all of that possible and having so many doctoral students come see campus, see a little bit of Nashville, and get out of the rain. I think the rain cleared up by dinner. please connect with us. We have an on-site WhatsApp group chat. If you'd like to text me directly and have your questions answered semi-publicly, please. The first link is for that, and we can also chat with people if you want to see what people are doing or coordinating with just generally this room. It's there. It's easy to mute if you don't want to have the live stream of ding, ding, dings like my phone. Alternatively, if you'd like to stream what you're seeing now, you can. Or if people are not here that would like to see like your labs back at home, you can say, hey, I just saw it on YouTube, and text them this link. There's no registration required. Now, since we're talking about Wi-Fi, VU Guest is the open network, and there's just an accept credentials pop-up. It seems to be working. I haven't had anybody have any problems so far. And if you are from a university that supports EduRoam, we have EduRoam, and then that will, quote, seamlessly integrate with your home credentials and your academic subscriptions and that kind of thing. Either way, I prefer VU Guest, but at the end, we're here for you. We're going to be at the registration desk. If there's a problem, we'll make it not a problem. It'll be good. And thank you so much for all of our volunteers. This has been a tremendous amount of work and a tremendous amount of joy of getting to know people and see people's talents and see people's problem-solving abilities. So thank you all. Thank you for coming. And let's start this party. Benoit? Wasn't the next thing the photo that you wanted to take of everybody? I was told to pass it back to you by Daniel.
I think going to take the first session.
Great. Go right there.
First speaker? Do you want to announce the first speaker?
Yeah. So hi everyone. Our first talk will be Super Mask. Introduce yourself. Yeah. Okay. Hey. Yes. So I am Oel Karvadek. I will be co-chairing this session with.
So I'm Gordon Wu from UNC Chapel Hill.
Okay. And yeah, bit of a rough transition, sorry for that. So yeah, our first talk would be, is entitled Super Mask, Generating High-Resolution Object Mask from Multi-View Underlying Low-Resolution MRI from Hongxue Gu. That is just here, so now please listen to her, and it will be very interesting.
Hi all, I'm Hongxue Gu. I'm very glad and feel honored to stay here to present my work on Super Mask. I'm a third-year PhD student from Duke University ECE department, and I have a fancy now my method, but just want to make it attractive. And here is my background. This is the background of this algorithm. MRIs as a non-invasive and low-radiation image technique is very popular in medical imaging field, and especially in our deep learning medical imaging area, like the MRI segmentation is crucial to extract image features, search the medical records, and enhance our understanding of human disease, and make accurate diagnosis. Here are some examples of MRI segmentation research, like brain segmentation and the radius cardiac segmentation. However, the current challenges, what is the current challenges for MRI segmentation? Like, we usually think MRI is a 3D volume image, but actually, in practice, they usually do 2D acquisition. What is MRI scans are done with relatively few slices and are significant slice thickness. So instead of like the volumes like the 3D volume we see, like in the middle of the right of the middle, like to see the real object, the MRI is like taking like a few slices, and between each slice, we have a gap between each slice. So it is more like the right side, like we sample each slice's object, and each slice we have a gap, and each slice we have a thickness. This is like normally do 2D acquisition instead of 3D high-resolution isotropic MRIs. So what is the percentage of like proportion of 2D MRIs and 3D MRIs? I calculate that. Like I collect all the MRI exams from Duke Health System since 2015 to 2020, and including all exam protocols. For different body parts, we can see that there is a very limited and few acquisitions are 3D MRIs. A large proportion of them just 2D MRIs. How the 2D MRIs look like? If we show the example, like it's like our students manually annotate the 2D MRIs in 3D slicer, and we can only, there is only that the in-plan view, it is high resolution, and the two other views, they're just like very coarse and low resolution. If we segment this object, and we how to click? We rotate it, we see it in 3D view. You can see that it is really coarse and at low resolution, and it's like grid look like shape, and we cannot see what the details of the bone. There is another example. You can see that it is a shoulder MRI, and if we segment the bone is just like grid look like a very coarse shape. If we manually segment, even very carefully and detailedly segmented, like we cannot see what's the accurate shape of this object. If we want to analyze some diseases such as bone instability, the bone disease and stuff like, we cannot know what's the real shape of the bone, what's the joint distance, and how the object actually look like. So it is challenging. So it is challenging, like we can only refer to in-plane slices, and the slow plane slices is low resolution. If we direct segment this object, it looks coarse and low quality. Our target is like, if we can only use the low resolution MRIs like to reconstruct and to recruit the high resolution objects without need of the high resolution images in the training stages. Thankfully, though we don't have 3D MRIs, multi-plane MRIs are commonly applied in clinical practice. What is multi-plane MRIs? Is like, we are not doing the 3D MRIs, but we do 2D MRIs at different orientations. Like, this is an object. This is, if we want to do an arm MRI, like, this is the axial view of the, like, we are cutting pieces in this way. And if it is a sagittal view, we are cutting pieces, like, in this way. Even at each view, they have low quality, but they at least give you different orientations to see this object. There are some previous works also trying to learn from multi-plane low-resolution MRIs to give us a better quality segmentation, object segmentation. Like this work, we show that they segment at different views, and in the end, we're trying to integrate or fuse the objects together and to give a better segmentation. However, we found that the previous works might be impractical because the current MRI high-resolution recreation methods from multi-planar views often require these three views to be well registered and near perfect orthogonal to each other. Like they ideally want, like, the object is not moving, and I'm taking different views, and I segment them, and I directly add them or use any way like property or to add them together, I can give a better segmentation result. But actually in clinical practice, the different views is more like is referred to the anatomy or coordination system instead of the word coordination system. What means? Like the object might just change the location, change the position during the views. These are the 3 4 MRI views we get from the single exam of one patient. This is axial view, this is chronal view, this is sagittal view. Like the patient takes 3 exams, 2D exams at the same time. And if we just integrate these 3 segmentations, we find that they are different positions, different locations. That if we just like add them together or using anything to fuse them together, they are not registered, and it not help us. So in order to recreation high-resolution masks from multi-view MRIs, we feel like image registration and alignment are necessary. Some previous studies also mentioned that, like, we noticed that these images are not registered, so we do some traditional registration as pre-processing, trying to align images together and match objects together. But generally, there are 2 steps, like the image registration and the downstream tasks are separate to each other, and the traditional iterative registration methods are slow. And so what we want in our algorithm is like we want to introduce an algorithm that can automatically register low-resolution, unaligned 2D MRIs obtained from different orientations and produce high-resolution objects directly. Here is the pipeline of our algorithm. It looks complicated, but it actually has like 3 stages. The first is the training stage 1. It is like pre-training. And the second is like I'm trying to combine the registration and the segmentation together. And the third is the inference stage. I'm trying to fuse the segmentation from different views together. In the training stage 1, is like I'm training a 3D registration network and a 3D segmentation network separately. Like in the registration, I have a moving image and a fixed image. Like I'm trying to transfer the pulse of the moving image to the fixed image using image coloration. And in segmentation, it's just a 3D unit. In stage 2, I'm kind of like trying to combine these 2 parts with 2 extra loss functions. The first constraint loss function encourages the segmentation network to predict masks from a single view of the image that looks similar to those of the image from aligned images. So the first construction is like I'm trying to encourage the segmentation network by the registration network. The second, the loss function is like I'm encouraging the registration network to align the segmented masks to have more overlap each other. So on the second part, like I'm trying to use the segmentation network to promote the registration network. So kind of during this iterative way, like these 2 parts work can promote each other and help each other to give a better result. In the third stage, it's just like how I fuse 3 views together. Is like I'm using the probability and with the uncertainties of like one under a Gaussian distribution. Here is like the experiment setting. I'm using 2 data sets because if we want to test this algorithm, we need to have high resolution objects to compare with, like how our reconstruction actually looks like. So I'm using 2 data sets. One is the brain MRIs, one is the heart MRIs, where like the high resolution MRIs usually available. And I'm like I'm creating the algorithms, like the experiments on 2 settings. One is like the different slices have distance of 8 millimeters, and another is like under 60 millimeters. It's like I sampled each 8 slices, or I sampled each 16 slices. Like for 16 slices, kind of a very extreme coarse image to reconstruct. I compare my method with several baselines. First is like I only use UNet to segment on low resolution MRIs. Then I compare with several settings of like I pre-registered, use traditional image registration method and to using segmentation, or I segment it first, then to trying to register all the segmented masks together. And also the last one is like I'm trying to train it on the high resolution 3D MRIs. And the last one is kind of the upper bound of this algorithm. It is not fair to compare with our method, but like we can know how our method achieved. And these are the metrics we use. Is like for segmentation, comparison is dice coefficient, under segmentation, over segmentation, root mean squared error, and also the boundary accuracy. I'm showing some results of our reconstruction. And this is like if we segment the low resolution MRIs, these are some results generated from traditional methods and some other methods. And here is the recursion of our method, and here is the recursion from the results directly get from high resolution 3D MRIs. We can show it here. Like here is like what's the segmentation directly get from low resolution 2D MRIs. Here is like our reconstruction results. Here is the real object in 3D, like real 3D object. We can see that our algorithm actually gets like more details of the object. It is not just like smoothing the low resolution objects. Like it can actually learn more details about the shape and to learn how the real objects look like. And there are some experimental results, and we found like our algorithm can improve the performance a lot. Yeah, it's almost done. Sorry. Like it can improve the performance a lot. We evaluated in different metrics, and we found that our algorithm can improve the performance a lot, especially when the resolution is super low. And there are some limitations of our work. It's like we only test two data sets at this moment. And we want to also extend to other body parts where maybe high resolution MRI is generally not available. And we are trying to compare it with low resolution MRI and CT images. And that's all for my presentation. And thanks a lot for your listening. And here is all the pictures of like code of our lab site and the code for my lab Twitter and the picture of my lab and the picture of my alien cat and the GitHub repository of this code and my social media. Thanks all.
Okay. Well, thank you for the very nice talk and very nice work. It was really very impressive results. So we're a tiny bit behind schedule, but we have a bit of time for questions. So if you have a question, you can go to the 2 microphones. And at worst, there will be also a poster presentation, so you can go to speak directly. But hey, please ask your question.
Hi, just to start it off, I think you really have the best layout of slides for the conference so far, so my compliments for that. Now, I really appreciate your work. I really wish to talk offline with you as well. Maybe a small question. In the old days, before deep learning, there were like other methods proposed. One is called SVRTK, so Slice to Volume Registration Toolkit. Is your aim to reduce the processing time, or do you also wish to outperform in terms of segmentation quality compared to the all-day methods? Is that clear to you? So are you faster in reconstructing and segmentation, or are you also doing better? Are you also outperforming conventional methods?
Yeah, we found that our algorithm have like faster speed and also have better reconstruction accuracy compared with traditional iterative method. I think it's because like the segmentation also promotes the registration network to have a better result. Yeah.
That's a clear message. Thank you.
Thank you.
Okay, so let's thank the speaker for her presentation.
All right, we're going to start our second wonderful presentation. This is the topics on the radiation oncology. So this is the work from the Netherlands. So the speaker will be Monica. So the floor is yours.
Thank you. Hi, I'm Monica Grewal. I will be presenting our work on learning clinically acceptable segmentation of organs at risk in cervical cancer radiation treatment. A brief background on this: cervical cancer, we know it's a type of cancer that affects a lot of women worldwide. And radiation treatment is the type of treatment that kills cancerous cells by exposing to radiation. One of the key goals of radiation treatment is to spare healthy organs around the tumor. These healthy organs are called organs at risk. During the treatment planning, everyday radiation oncologists and radiation therapists, they spend a lot of hours in contouring these organs at risk so that the information can be provided to the dose delivery system. So our motivation behind this work was we can probably use deep learning to automate this process of organs at risk development, organs at risk contouring. So the story goes like this. We had access to 105 CT scans from cervical cancer patients in a local hospital, and we had access to their clinically available contours. If we had gone by a traditional method of deep learning development, say we chose to do a 70-30% split between training and testing data, we had around 73 scans for training and 32 scans for testing, which is not a lot. We cannot do a lot of things with a limited training data set unless we go with pre-training methods and self-supervised methods. And with the limited testing data, we cannot say our results with confidence because we tested on only a limited data. B, we will always be wondering if it was a lucky split or if it was a very unlucky split. So there could be many other approaches to deal with the situation, but the idea that we came across was we reserved all of this data for testing, and we looked for training data elsewhere. Specifically for training, we looked for scans of female patients who were treated for cancers anywhere in the abdominal cavity. And with this search criteria, we got a lot more scans with their clinically available annotations. So we were happy. We had a large training data set and a decent testing data set. But then came the realization. First realization was because the data was coming from a very loose search criteria, it had a lot of inhomogeneity in terms of the scan and the extent of the scans in the cranial caudal direction, and in terms of the extent of the annotations, because the annotations were made for clinical purposes based on where the tumor was located. And the next part of the realization was, even though we had 1170 scans, when we looked for scans that had annotations for all the organs at risk that we were interested in, we were left with only 186 scans. Rest 84% of the scans had missing annotations in at least one of the organs. So what did we do? First, we did the hard part. Well, we didn't do the hard part. We did it smartly by developing some heuristics. We looked at the training data sets and developed heuristics for automatic data cleaning. And these heuristics included whether to discard some of these scans or how to crop some of these scans where the extent was extending to the chest region, and delete annotations in non-relevant regions. Next, we developed an approach. This is an overview of our approach. In the next slides, I will be going through the 3 steps one by one. So in the first step, we trained a teacher model, a K-head teacher model, and the teacher model was a 3D unit. And we chose K-head version of it so that we could calculate uncertainty of the predictions. I will come back to the uncertainty part later on. We trained this teacher model on the small fully annotated data set to generate predictions on the of organs at risk. In the next step, we used this trained model to impute the annotations in the missing annotations data set. Briefly, on the left you see an image from the partially annotated data set, and in the bottom the available label is the clinically available label is shown. Yellow is rectum and blue is hip, and the contour for bladder is missing in this image. So we use the prediction of the trained teacher to impute this label. So we use for bladder, we use the prediction from the teacher. For rectum and hips, we keep the original clinically available annotation. And we calculate entropy of the predictions and call it uncertainty. In the next step, we train a student model, which is an exact replica of the teacher model, on the full data set, which included both the fully annotated data set as well as the partially annotated data set with imputed annotations. So the training of student is slightly different than training of teacher. In the training of student, the uncertainty, the cross entropy loss is weighted with the uncertainty guided weight. And the way this uncertainty guided weight is calculated is wherever the teacher model was highly certain about its predictions, the uncertainty guided weight is high. Wherever the teacher predictions were uncertain, the weight is low. And the reason for calculating this weight is in this way is we want the student model to learn from the available annotations in the large data set while minimizing the deteriorating effects of the imperfections in the teacher predictions. So then the question comes, did it work? Well, if we look at the contours generated by one of our model in the bottom row and compare them with the contours that were available clinically, so they were generated by a radiation therapist and then confirmed by a radiation oncologist. The contours red for bowel bag, green for bladder, blue for hip, and yellow for rectum. These contours look quite similar, so it looks like it worked. In numbers also, there was a significant effect of automatic data cleaning. And then there was a further significant improvement of our proposed teacher-student model. Mind it, in this, the second row corresponds to a 3D unit trained on a fully annotated data set. The 3D unit was hyperparameter tuned, so it is at the level of NN unit. So it is comparable to if we had, say, taken this limited data set and trained a NN unit on this. And there is a significant improvement on this performance with the same model, with the same 3D unit. Then the next question comes as, how good is this performance? If we compare the numbers with the numbers reported in the literature, it is as good as state-of-the-art. And I have highlighted the best numbers for all the organs at risk. You see, the numbers are not only the numbers are comparable with the state-of-the-art, but our results are more reliable because we are reporting it on a comparatively large data set compared to many other state-of-the-art approaches. Then the next question comes is, does it help the clinicians after all? To answer this question, we took contours of first 4 scans in the test data set, and we showed it to a radiation oncologist along with the contours that were clinically available on those 4 scans. And we asked the radiation oncologist to grade these scans in terms of their clinical acceptability. And these were the results. So the grades were basically, grade 1 represented that the contour is acceptable as it is. Grade 2 in blue represented that the contour is acceptable as it is, but the radiation oncologist differs in the way the contour has been made. So it's anatomically accurate, but the radiation oncologist thinks that if he or she would have contoured it, it would have been slightly different. And grade grade 3 it requires a minor correction because it combines a nearby tissue in it, or it doesn't cover all the tissue in the organ at risk, and grade 4 is not acceptable. And the results were, the first results were none of the contours were given grade 4. That means all of the contours generated by our model were clinically acceptable. And next, we could run statistics on bowel bag, bladder, and hip histograms. The histograms for bladder and hips were not statistically different between the automatically generated contours and the manually generated contours. The histograms were different for bowel bag, but if you look at the graphs, it is difficult to find out which of the contours were better, because automatic method gets higher grade 2 rating and lower grade 3 rating, whereas manual contours got higher grade 3 rating. And this difference basically comes from whether mesorectum was included in bowel bag or not. And for rectum, we could not do statistics, but if you look at the graphs, they look quite similar. So we can say that the clinical acceptability grades were similar for both type of contours. So in short, we want to say that state-of-the-art and clinically acceptable performance for organs at risk in cervical cancer treatment can be achieved with the simple model and with using only the clinically available data, despite label inhomogeneity and missing annotations. But obviously, the story can always be better with inputs from my peers. Thank you for your attention. I'm open for questions.
All right, very nice talk. Any questions from the audience? Yeah.
Hi. Thanks for your presentation. I was curious, did you try anything else besides entropy as an uncertainty measure?
No, I didn't. And the reason, no, I didn't.
No worries.
Yeah.
Yeah, I don't know if Monte Carlo
Yeah,
dropout
because
or
it was the main focus was not we want a good measure for uncertainty. The main focus was something else. So it was an auxiliary objective.
Sure. Yeah. No worries. And one other question. Was the teacher trained first, or was that the expected moving average of the student, or how did you train them separately?
Teacher, it was trained in a sequential manner, iteratively, and I didn't mention that we did 3 iterations of this teacher-student training, and the way it differs from existing methods is that the student was trained from scratch. Yeah, not fine. So even though the student model is same as teacher model, it was the teacher model was not fine-tuned. It was trained from scratch.
Gotcha. And was that, did you use some sort of pre-training or random initialization?
No.
Sure. Cool.
Yeah, so if we would have, say, fine-tuned the teacher, we could call, say, we are pre-training the teacher model, and we, in our preliminary results, we observed that pre-training and then fine-tuning the teacher with imputed annotations yielded poor results. Gotcha. Than the reported ones.
Awesome, thanks.
Well, thanks for your excellent talk. I'm really interested in your approach to dealing with missing and incomplete data. I think this is a really relevant issue that we all have to address. I'm really interested in your use of this uncertainty that you explained. Did you also do experiments in taking your labels just as is without any measures of uncertainty, and what kind of results did you get there in comparison?
Yeah, thank you for your question. We did these experiments. First experiments were, can we just do a masked back propagation? Can we just make use of the labels wherever they are available and leave the rest? That was poor, I think, because the supervision became sparse. And next experiment were, can we use the pseudo predictions, the probability as soft labels? And that was also poor than the uncertainty guided weighted training. Yeah.
Okay, thank you very much.
Great, so we're right on time, so thanks. And so we'll for
So we'll have some teasers video presentation now, before a bit later the middle board special session. Thank you.
All right, so if you are a teaser speaker, you should have received an email this morning. Please come up to these seats in the front, just so that we can be efficient about this. We have 16 in a row this morning, so if you really don't like it, please let me know immediately, and we'll modify it for next time. Right. And the first speaker will be P016, or P16.
Good morning, everyone. My name is Amanda D. I am from Toronto Metropolitan University, and my research revolves around developing deep learning techniques for clinical pathology. Quantifying biomarkers for breast cancer detection is laborious, it's expensive, and it also leads to very subjective results. Deep learning can definitely help with this, but it often struggles with out-of-domain data. To counter this, we have proposed a domain adaptation pipeline that uses both silver and gold standard labels. We use an unsupervised method to generate noisy labels from our target sites, and we use these to pre-train our network. So by doing this, we are able to address the data scarcity problem and also increase our model robustness. So our results do yield, they do outperform our current gold standard, and they offer an efficient calibration method to enable large-scale deployment of AI tools into digital pathology. So I look forward to discussing my work at my poster presentation. I am M15. Thank you.
Thank you. Our next speaker is P033. Are they present? Or possibly stuck in New York? Unless they come up, we can circle back to them, but the next speaker will be P073.
Good morning, everyone. If you are interested in explainable AI in medicine, please check out our poster on HNIT. In this work, we propose an inherently interpretable multi-label classifier for chest X-ray classification. The explanations from HNIT are faithful, trustworthy, and human understandable. I'm looking forward to see you there. My poster is at location M19. Thank you.
Thank you. Our next speaker is P133. Oh, sorry, P078. My apologies.
Good morning, everyone. So the goal in the clinical MRI setting is to go as fast as we can from scanning to an accurate, high-quality reconstruction and segmentation. Usually we think those two tasks as sequential tasks, but there is always a task relatedness, meaning that segmentation is always dependent on the reconstruction quality. Does a direct forward exist? Can we go from our acquisition directly to our end goal? Multitask learning allows us to use feature sharing and optimize for both tasks by training models at the same time on the number of tasks we want to optimize as our end goal. Performance is improved by sharing features and implicitly informing them as inductive biases. If you want to learn more how multitask learning works, and if you want to see how well it performs compared to other methods, please visit my poster at M20. Thank you.
All right, thank you. And our next speaker is now P133.
Good morning. I've investigated the reproducibility of training deep neural networks. So what we did is we took a couple of established neural networks that were already published and just retrained these a couple of times. What we observed there is that there was quite a lot of performance variations between these different training runs of about plus minus 1%, which is quite similar to what is often published as the improvement of a particular new training method. So if you don't take this into account, what you then can get is that your results are invalid. This is exactly what I've looked at. So if you want to talk more about that, meet me somewhere. I don't know where.
Thank you. P212. Is there a speaker for P212? Seeing as they're from NYU, they may not be here. So we'll move on to P229.
Hi, everyone. I'm Joey Sprong, and I'm happy to show you my work. In our work, we bring NNUNet to the field of pathology. So what that means, as a pathologist, you can eliminate the hassle of going over hyperparameter adjustments and eliminate the hassle of going over optimizing your training pipeline. In our work, we showed that we changed a few hyperparameter trade-offs. We integrated a much-needed whole-slide inference pipeline. And next to your segmentation output, it gives you your uncertainty heat map as well. So you can use that for your downstream evaluation. We validated our changes using by testing our performance on the Tiger Challenge. We immediately got the first place at our first try. So we think that was a nice validation, and it shows the potential that it may have for our field. So if you're interested, I'm happy to talk to you and have a nice discussion. My poster will be on the session on your right. It's the first poster, and I'm happy to have a discussion with you. Thank you.
Thank you. And now for P238.
Good morning, everyone. My name is Janmesh. So I'm presenting localization over statistical shape modeling. So statistical shape modeling is an important for characterizing anatomical shape variation and morphology. So it has various applications in like orthopedics or implant design and growth modeling. And the typical way to do is using a particle density model, where we define like a correspondence across the population or shape. So in the traditional approach of doing this is first getting segmentation from images, and then performing registration, image processing, and final generating correspondence, which is time consuming and involves a lot of parameter tuning. So we present localized SSM, which generates the correspondences directly from images without any pre-processing. Please visit me as M32. Thank you.
Thank you. And now for the short papers, S001, Dr. Kai.
Hello. Oh. Hi, everyone. My name is Leon with S001. And so as deep learners in medical imaging, we do a lot of convolutional networks, transformers to translate images or classify them. But for this work, we describe this new framework of using RNNs to propagate something through an image instead. And so we're doing this specifically looking at white matter pathways in diffusion MRI, and are really excited to see how this sort of translates our diffusion MRI paradigm. So I'll be at, I guess, M33 over there, so come hang out. Thanks.
Thank you. And now for S033.
Hello, I'm Alexandra Wolter from the German Cancer Research Center, the Karlsruhe Institute of Technology, and the Helmholtz Information and Data Science School of Health. I'm actually working on clinical target volume segmentation with the additional help of mathematical constraints extracted from expert guidelines. These expert guidelines describe target volumes by surrounding anatomical structures. So as an intermediate step, I segmented 71 anatomical structures that haven't been segmented before. Like most of them have never been segmented before because they are no organs at risk and no target volumes, so not of interest for actually clinical use. If you want to talk about a world in which we can segment every structure in a human or clinical target volume specifically, please visit me at my poster on that side, location M39. Thank you.
Great. And our next one is S049. Hervé.
Hi, hello. I'm here on behalf of Melanie, who couldn't come, so I'm her colleague, Hervé Lombard. And we wanted to share today about stochastic active learning for segmentation and not necessarily for classification. What if, for example, you're given an image, a data set of, I don't know, thousands or millions of images? Which images to annotate first? We often take this for granted. But yeah, either you select all images together or you select them smartly, let's say. So that's poster M42 if you want to know a little bit more. And I don't think it's that side. In fact, the poster are on that side, right? Cool, thanks.
S062?
Hi. So if I knew that there would be a presentation, I wouldn't have taken like half of the slide for the title. So in our study, we wanted to evaluate like anomaly detection, and localization is like quite a promising approach for many tasks in medical imaging. And but there's still a quite high domain or like performance gap to supervised methods. And we used a like well-established method for anomaly localization that also scored quite well in the mood challenge, and used this like to compare to supervised methods, and also to use this as a like a pre-training for a unit in a supervised setting, and then compared to the baseline and like showed how it compares to a pre-trained model. And for our test case on the Brett's data set, it also outperformed like the baselines. But you can also see here in the graph, for example, that with quite a few training samples, you can also like outperform the unsupervised method. Yeah. If you want to talk about it, meet me in this room, or on Wednesday also, we have another poster. Thanks.
Thank you. And now S062. Oh, sorry, that was the previous one. S071. All right, present. Okay, we may have to circle back to them. And M51 or S119?
Good morning, everyone. So I want to bring you to the attention of the levator-ani muscle avulsion. It's basically a tear in the levator-ani muscle in the pelvic floor. When this tear happens in women due to childbirth, it can cause many different issues, such as pelvic organ prolapses and urinary incontinence. So it's a very detrimental thing to their quality of life. So the diagnosis is in about 36% of women, and many unreported cases in developing nations. So what we have done in this groundbreaking study is utilize deep learning-based methods using UNet, and brought it to 3D endovaginal ultrasound images to segment basically this levator-ani muscle. And we got amazing, amazing performance. So eventually, we're going to bring it into AI diagnostic tools to deploy to developing nations. So if you're more interested in learning about this, meet me at M51. It's in that location over there, and we'll be happy to discuss more. Thank you so much.
Thank you. And let's thank all 16 of the speakers, or 13 of them, one more time. Okay, so at this point, we're transitioning into the special session. So we'll have an introduction about this session, and then we will have 2 presentations from it.
One from Alessa, not the from.
Yeah.
Exactly. Thank you. Thanks. Yeah, hi, and I'm happy to also welcome you in behalf of the MIDL board to this year's MIDL conference here in Nashville. And first of all, I would like the conference organizers for this amazing organization, so thank you. And in this session, Bram and I will give some information from the middle board before we have 2 talks about reproducibility and the Pikai challenge. The middle board has grown in the last year since Emma, Matthias, and Ismail have joined the board. And most of us are also present at the conference, so if you have any ideas, comments, something you would like to discuss, look for these faces walking around here and contact us. But you also find more information on the general middle website. So not the website of the conference we have browsed quite often in the last days, I guess, but the general website, because middle is not just a conference. Middle has, of course, the main event is the annual conference to meet and present the latest research. However, next to it, we also have young researcher events like the doctoral symposium yesterday, which was, again, a great success. So also thank you for that organization. But also during the year, we are aiming for multiple events to connect the community via online events and challenges. We are aiming for 4 events distributed over the year, which have different target groups in mind. So currently, we have named them Autumn Academy, Winter Workshop, Spring Symposium, and yeah, well, Summer something. We have to come up with a better name, so when you have one, let us know. And for example, the Autumn Academy could be about how to set up a challenge, or another tutorial on how to use transformers, so all that kind of things. We thought of a winter workshop for more younger researchers, so the PhD students, with topics like how to write a great paper or how to write an outstanding review. However, those are just ideas, and we are very happy about your ideas. What do you like? That's very important. So for example, last year, we were contacted by Attila, who has been working on reproducibility of methods submitted to the middle conference as a paper. And subsequently, he gave a very informative tutorial on how to make your research reproducible. He presented that at the Autumn Academy. His work and the tutorial were the starting point for the middle guidelines on reproducibility, which you now find also on our website. And because of that, we invited him to also present his work in this session. And I think that very nicely demonstrates that everyone who has an idea and who wants to do something can impact and shape middle, the conference, but also the community around it. So if you have any ideas for tutorials or other events, check out our virtual event guide that we wrote and contact Janus and me. So at the moment, we are the 2 people who are organizing that, but it's, of course, a lot of work, and we are very happy about everyone who wants to get involved. Even if you just have an idea what you like to have as a tutorial, let us know, then we can see what to do and maybe reach out to some other people in the community and ask if they could do this kind of workshop for you.
Yes, and another thing we have started with are middle challenges. As you know, challenges are very popular in the field and also very important, driving forward the research. And we want to organize a few challenges in conjunction with middle every year. And if you have any ideas or proposals, there's a call on the website, and please approach us. Now, what a lot of other conferences do is that at a conference there are workshops for challenges. Sometimes many workshops, and actually I personally think the idea that all these researchers all over the world travel to one place to have a small workshop of an hour to meet each other about a challenge is something we shouldn't do. I think challenges are very well suited to be run online. So we teamed up with grandchallenge.org, and we want to support challenges that are actually just running online. And we want to focus on challenges that really want to make an impact so that the solutions of the challenges can also be used by others to move the field forward. That's very much in line with the open, reproducible, transparent way of working that we're trying to promote at Middle. So we will only support challenges that have data that is completely open, and the participants should make both their training code and their inference code also completely open so that others can learn from that and take advantage from it. And if you have that, then also the actual challenge solutions can just run online on Grand Challenge. So everybody is then able to upload their own data to see the result of the solutions that have been developed during the challenge. And what we also want to do is we want to give people who do very well in these challenges the opportunity to present here at MIDL. So we'll have brief overview talks of these challenges, and we will have one from the Pikai challenge in this session. But I hope that next year at the conference in Paris, the best performing teams of the Pikai challenge will be able to present their work at MIDL. We've also already started such a collaboration with Melba, an open journal in the field that has very similar aims to what we are trying to do at MIDL. And actually people who publish a journal publication at Melba, they can give a presentation of their work at MIDL as well. Because why write another conference paper if you have already written a very nice journal paper? So these are some of the new initiatives that we're trying to encourage. And if you have other ideas for things to make MIDL a more interesting community and conference, then indeed, please contact us. So I would say now, let's go to the first special paper in this session on reproducibility.
We have to believe that we trust you here, just in case.
I accept.
Thank you. Hello. So my name is Attila. I'm from Umeå University in Sweden, and we would like to bring your attention to reproducibility at MIDL. Since its start in 2018, the MIDL community has been committed to openness and transparency. All right, sorry about that. But it's not well defined what this means in practice. However, we will see later on that the majority of the full paper submissions aim to produce reproducible results. And the papers presented in the next few days can be detailed and thorough, but we as readers will know well enough that the main body of the paper is often not enough to be able to reproduce the results. This is partly because in deep learning, the smallest of details can make the difference between state-of-the-art and just pure garbage. And also, with the 8-page limit, it's really almost impossible for most of the papers to describe everything in sufficient detail. So, as the research field matures, the solution proposed to this issue is code sharing. So you can just publish the exact same code that you used during your research, and others can hopefully go and reproduce it. This is using repositories like GitHub or Dropbox. However, at most venues, this is not part of the review process. So they have no immediate impact, and therefore, understandably, their quality is often overlooked. So what we did is we collected guidelines from other journals and conferences, and then we systematically evaluated all of the full paper submissions from MIDL since 2018, and we used those results to set up a guideline to help future authors publishing their code. So we can get right into it. From the manuscript, we have 3 expectations from all authors regarding reproducibility. The first one is that all authors should explicitly state what material they used is public and what's private. Additionally, the authors should aim at using public data sets, and they should be referenced appropriately. And also, they should aim to make their code public, which should also be referenced appropriately. Then we can go into the subset of the papers that actually have code repositories, and those repositories can be further evaluated. If we go into that, if you are running the code in a new environment, a list of packages first need to be installed. This list should be present in the repository. If you propose a state-of-the-art model, then we encourage you to also share the model weights, so it will be easier for future papers to compare their methods to yours. And the code for training and for evaluating the model that you propose should also be easy to find just by going to the repository. And additionally, all of these points that I mentioned before should be easy to find on the documentation for the repository, which should also have licensing in place. As you can see, this guideline is nothing novel. It's really just a set of expectations from a code repository. They're all pretty straightforward. And what we can also do is we can use this guideline as a checklist to evaluate all of the papers submitted to MIDL. So that's what we did, and we collected our results here. What we're most interested in is to see any trends, so we categorized our results by years. We can go through it step by step. So we see an increase in the number of submissions, which just purely shows that the conference is growing. And we also see a steep increase in the use of public repositories, which is great, and it shows that code sharing is becoming a standard in this field. And there's also an increase in the use of public data for evaluation. But if we go into the repository-specific evaluations, the results are less encouraging and optimistic. Around half of the repositories don't mention what kind of dependencies they used to run their code at all, which makes them really difficult to use, especially as the years pass and the packages change. The training and evaluation codes are generally easy to find, so that's good, but also only around a quarter of all repositories report the actual model weights that they report in their papers. We also find great insufficiencies in the level of documentation and licensing. And most importantly, there seems to be no trend in their quality throughout the years. This average score is the reproducibility score that we can assign to all of the repositories based on how many boxes they ticked in the repository evaluations. We also evaluated this year's results, and to double check, I double checked last night just to make sure that everything is up to date. But before I do that, I would like to jump back a year and discuss a little bit about what we did since the last year. Alessa already kind of spoiled it a bit, but we contacted the MIDL about what we found, and they gave us the opportunity to present at the Autumn Academy. And the discussions gave us plenty of ideas on how to move forward, and there were also numerous suggestions on how these guidelines can be improved. For example, the licensing option is something that was added after the Academy. So my main point with this is that this is really a community-driven, living, breathing sort of document, and it should be treated as such. And it's not a concrete set of requirements that all of the papers should follow. It's more just a guideline to help authors publishing their code. We also understand that for various reasons, not all questions are applicable for all of the papers. And since all of the evaluations are public, I would like to point out that a low reproducibility score doesn't mean anything about the critique of the work. So reproducibility is really just a small but critical part of your research. So if in the case of a low reproducibility score, you can disagree with our evaluations, and then we can discuss it at the poster board there. Or you can agree with our evaluations and keep in mind that changing the code repository is really much more straightforward than changing your actual published paper. So it's not really a large issue. And to provide additional motivation for authors, we also had more real-world interpretation of our results. So we created this graph where the average number of citations for each individual paper was collected from Google Scholar, and we plotted it against these assigned reproducibility scores. And we can see that well-maintained repositories usually belong to well-cited papers, or alternatively, that well-cited papers generally have well-maintained repositories. So after a year-long journey, we were really looking forward to this year's MIDL to see where the results go. And again, there was an increase in the number of accepted papers compared to last year. There was also a slight decrease in the ratio of public repositories, but the use of public data is still really encouraging. And as for the repository evaluations, I have to report that the results are really worse than ever. So compared to last year, all of the individual evaluation metrics decreased. And to kind of point out the significance of our concern, we can kind of clarify a bit what these numbers mean, doing a bit of math. If we take the evaluation of the dependencies for an example, we can see that the results are kind of similar between 2018 and 2023. Around 50% of all of the code repositories correctly reported their code dependencies. We can look at this pessimistically and say that 50% of the repositories had some kind of issues reporting dependencies. However, with the conference growing and with the ratio of available code repositories, this means that in 2018, there were 47 papers. Out of those, there were 14 repositories, so we found issues in 7. Whereas in 2023, we found the same types of issues in 32 repositories. So the results are not improving, but the problem itself is sort of getting bigger. There is one silver lining, is that if we look at the average score, we can see that there's a much larger standard deviation for this year compared to previous years. This is because out of the 72 code repositories for this year, 18 are still completely empty, probably with the authors hoping for their papers to be published first before actually publishing the code. And this is completely understandable because you can just revisit these evaluations so we can perform them in a few months and hopefully the results will be better. But I should warn you that there are also completely empty repositories for papers from 2018, so something to keep in mind. We hope to encourage you to take a second look at your code repositories if you shared your code in order to make your code easier for others to use. I hope I could kind of show that maintaining a code repository is worth your time and your effort. And we also hope that the guidelines can help you do so and just focus on what to pay attention to. Right now, it's a sensitive period regarding how AI is viewed by the public, so I believe that we have to do our very best to make our models transparent, our methods reproducible to build trust in AI. And the guideline can be found in full length on the MIDL website. You can follow the QR code for the full list of evaluations, and if you have any feedback, you can find me at the posters, and also just feel free to reach out in any way you'd like. And I have one last thing to add. I said that it wasn't our intention to evaluate the individual papers, but to celebrate the authors that went the extra mile. We have collected 2023's most reproducible repositories. So if you see your name in this list and your paper in this list, that means that you reached a reproducibility score of at least 5. So first of all, congratulations, and also thank you. And feel free to drop by our poster for some chocolate. And with that, I would like to thank you all for listening.
Quite a lot to take into account when I now write the paper and I'm new in the field. What would you say, what should I start with to get it, my paper, my research reproducible?
Right, I think the most important is to figure out if you can share your code. Like if it's a transparent discussion between you and your supervisors and you feel like everything is publishable, then just create a repository and you can revisit it later if you hear any comments. So yeah, I think a lot of it comes from not knowing what you can actually publish and what you can't. So that's where it gets slower, I think.
Hi, thank you very much. My name is Jim. I'm wondering, do you have any idea, like broadly in the industry, kind of where these scores line up? Is there context, like compared to either other conferences or other published works more generally? How these scores reproducibility stack up?
I think MIDL has a really manageable size of papers and also code repositories, so it's easy to do these kinds of evaluations, but I don't think I have seen it for other conferences. If that was your question, I think, right. So I don't know, but I don't believe that there's a very big difference because I don't think there's a difference in knowledge if there's no guidelines to help the authors. But we looked at other guidelines from Pikai, I think, and NeurIPS, and they have now reproducibility guidelines as well, and they are fairly similar to ours, and these were just adjusted to better fit the issues that we found here.
Are there any further questions? No? So then let's thank the speaker again for the nice presentation. And let's hope that next year these numbers are increasing and getting better. And then we move to the next speaker about the Pikai challenge.
Hi again. On behalf of the committee of organizers and advisors, I would like to present you the challenge on artificial intelligence and radiologists at prostate cancer detection in MRI, or in short, the Pikai challenge. So to quickly recap the clinical problem at hand. So prostate cancer is a big issue, and MRI is playing an increasingly important role in the early detection and prevention of overdiagnosis of these patients. However, the current MRI interpretation is semi-quantitative, which means that which leads to a large inter-reader variability and also to a lot of overdiagnosis for patients. AI has the potential to assist in this process, but currently lacks the scientific evidence for clinical translation at scale. So for the Pikai challenge, we actually set out to provide this clinical evidence and compare the performance of modern AI to radiologists worldwide. To do so, we first started out to collect a large multi-center and multi-vendor dataset of more than 10,000 cases. And then we used this dataset to set up a grand challenge with AI models. So while clinical trials are the gold standard for evaluating new drugs or interventions, the equivalent for AI model development is international tournaments, or so-called grand challenges. And so we've organized that. And in parallel to the AI challenge, we've also organized a reader study with readers from all over the world. And then the primary endpoint of our project is to evaluate the diagnostic performance of these AI models from the challenge against the readers from this reader study. So today I will focus mainly on the AI part. So organizing such a challenge can be done in kind of a different couple of ways, which are mainly characterized by what participants sent in as their submissions. So in so-called type 1 challenges, participants provide predictions for the test cases. And then the challenge organizers are tasked to take these predictions and evaluate them in a consistent manner for all participants, such that you get a fair evaluation of the model performance. But you can also go to the type 2, where you not submit the predictions, but rather the algorithms that you have developed. And then the challenge organizers are tasked to take these algorithms and automatically predict the test images. And in this way, you keep your test images private. So that means that you remove any potential bias, intentional or unintentional, from really seeing the test images. And additionally, it also makes the algorithms that are developed in your challenge available for use later on. So for example, on the grandchallenge.org platform. Then there's kind of a final type that you can do, which is the type 3, in which the participants provide not the algorithms, but really the training methods to get to these algorithms. So in this type, the challenge organizers are tasked to take this training method and then apply it to their data set. And in this way, you can also use a larger private data set for training, which has potential more sensitive information that you cannot make publicly available. Additionally, it also then makes sure that the training methods become available after the challenge completes, and then further research can be accelerated because you can immediately take that as your starting point. So in the Pikai challenge, we are committed to producing solutions that are reproducible and also public, which also makes us a good fit for being a middle challenge. And for that, we chose to first do a type 2 qualification phase, and then with the selected participants, teams, we went on to a type 3 phase. So a bit more on really the task for the teams. So in the open development phase or the qualification phase, the teams were tasked to take in a biparametric MRI scan of the prostate, along with some clinical variables, and then their AI algorithm had to predict non-overlapping lesion candidates, and also a per patient confidence score of that patient harboring prostate cancer or not. This is actually clinically significant prostate cancer, which would then also be needed to be treated. And then we compare that against the ground truth. So we have also collected just by waiting a bit and seeing what the outcomes were from histopathology, etc. And then we can compare the predictions against the reference standard and come up with a precision recall curve for the lesion level performance, as well as a ROC curve for the patient level performance. And for this, we've made a data set of 1,500 cases completely publicly available, such that they could use that for their model development and developing their models really. And alongside that, during the challenge phase, they were also had access to a leaderboard, so they could submit their algorithms and then get feedback from a validation set of 100 cases. And then at the end of the open development phase, there's the test set of 1,000 testing cases, including an additional external center from Norway. And each team could make a single submission to this test set, and then that's it. Okay, so then when we moved on to the closed testing phase, we didn't use just the 1,500 publicly available cases, but the full set of more than 9,000 training cases that were available. And based on the open development phase, we have selected then the top 5 teams there. And then we retrained each of the algorithms. So that means that there was no intervention from any algorithm developers here to really ensure full reproducibility of their training methods and prevent any potential bias from, for example, custom model selection, looking at the training curves, which you cannot translate to actual code, so then it's also not reproducible for other researchers. All right, and I'm very happy to share with you the final results for the Pikai challenge of the top 5 AI teams. So this is then again on the testing cohort of 1,000 cases. Here they are. So I understand that you don't necessarily understand exactly what an AUC of 0.934 means. But what I can already tell you is that we saw a significant performance increase when moving from the publicly available 1,500 training cases to the type 3 phase, where more than 9,000 training cases were available. And later we will also compare the performance of these algorithms against the 62 readers that have finished the reader study. But what actually made this top 1 team win this challenge? So their approach was relatively simple, actually. So what they did is they had the prostate MRI exam and first fed that through the NNUNet framework. So I think most of you are familiar with that. And then you get already the non-overlapping lesion detections. And as well as the NNUNet framework, they also used the NN detection framework to get bounding box predictions. And what they then did was they did a per lesion ensemble or regression to come up with the final confidence level for each lesion. And in this, they also included the clinical variables relevant for prostate cancer detection. And I'm also very happy to share with you that most of what we have achieved here will be publicly available. So for all of the submissions, there will be a grand challenge algorithm. So that means that any of you in this room, but also anywhere else in the world, you can upload your own data set and get predictions from these models. So they will become publicly available alongside the main paper. So you'll have to wait a little bit, but after that, everyone will be able to make their predictions. And also for 3 out of the 5 teams, both the training methods and the inference methods are completely publicly available. You can go to our challenge website, so that's pikai.grandchallenge.org, to get the overview of all of the training codes and inference algorithms, which will become also available after this talk. So if you don't see it just yet, that's fine. So then to conclude, I would like to thank our scientific advisory board. So we have had help from experts across both artificial intelligence, radiology, and urology who advised our study design. And these have really been instrumental in setting really the quality for the Pikai challenge. And also I would like to thank all of the 62 radiologists who participated in the reader study and providing the final comparison against the AI models. So then, next up for the Pikai challenge, so as I said also before, we will compare the retrained algorithms ensemble against the radiologists from the reader study. Submissions remain open, so if anyone wants to evaluate new models, then it's possible as well. And the lessons that we've learned from organizing this challenge will be presented in the MIDL online workshop in fall of this year. Thank you very much.
Okay, thank you very much, Juran, for wonderful results of a very impressive challenge. And I see there's a question already from the audience.
Hi, thank you for the talk. So, do you have a sense of what is the error of the radiologists' predictions?
Yes. So I can already tell you that it's in the same range. So I will not spoil the exact analysis of the comparison between the AI and radiologists just yet, because that will be preserved for the actual paper. But I think, yeah, you can be impressed by the performance of the AI compared to radiologists.
Yeah, but I was referring to the error just purely in the radiologists' like predictions, basically, versus the gold standard.
Ah, okay. I'm sorry. So prostate cancer detection on MRI is quite a challenging task. So that means that they often go for a high sensitivity to make sure that all of the cancers are found, but that also then results in quite some false positives. And what you typically see is that the sensitivity is about 93%, and the false positive rate is about 15%.
So given that you're the best performing solution achieved around 93%, 93 AUC, that's kind of reaching the limit of the accuracy of the radiologist per se, right?
Yes.
Yeah. So that's interesting. So we need to kind of think about in the future how to, go beyond that limit and so yeah, approach the gold standard. Yeah. But thank you so much. Yeah.
Thanks.
I also have a question. You said in your other paper that, so you look there on the training performance depending on the training run, so the random initialization of the model. Did this issue also apply for the methods that have been evaluated in the Pikai challenge? So if you would train all those 5 methods again, would the winner still be the winner, or is it then a different order, or might be a different order?
That is a very good point. So there is in principle no reason why these 5 teams would be any different from the ones that we have analyzed in that project. And given also that the performance of the different teams is relatively close, I would expect that if you retrain each of them, it will be just, again, a lottery. And I would imagine that the one that won now has maybe a bit larger chance of winning again. But in the end, I think what we can really conclude is that these algorithms represent kind of the top of AI, rather than saying that, okay, the one that has now the highest performance is the best and any other approach should be stopped.
Okay, thank you. Are there any further questions from the audience?
Well, I also have one further question. So it was very interesting to see that when you moved from type 2, where the algorithms were trained with 1,500 cases, to the larger data set of about 10,000, all the algorithms improved in performance, right? So that's encouraging. Do you think that 10,000 cases is enough, or would the most sensible way to get even better performance now be to work more on the algorithms, or to collect even more MRI data?
So what we have seen so far is that there's kind of a logarithmic relationship between the performance and the number of training cases. And personally, I haven't seen any sign of that slowing down. So that does mean that when we now have 10,000 training cases, to get kind of the next step, we will also have to get 10,000 more training cases. But I think that is definitely where we can get a lot more value still. And then at some point, it really becomes more of a question on how good you can fit to your training data set. But I think we are not quite there yet.
Okay, thank you.
If there aren't any further questions, let's thank the speaker again. And then we are right in time, or even a bit before our time, to close this session.
Exactly. So I know I'm standing between 200 jet-lag people and their coffee, so I'll be quick. Just a couple of quick announcements. So the poster sessions is next up, so either side. So the posters 1 to 30 on this side, 31 to 60 on this side, except a few posters that are still in New York. So we thank you for your patience for, while we're managing the flight issues. Second announcement, those of you who sign up for a VICE tour, my student David Liu is standing in the back, so that's going to be happening now. If you haven't signed up for a VICE tour, you can still do so. So David is going to be meeting you in a couple minutes in the front desk where the registration was, and he's going to be walking you over to VICE. VICE is our Vanderbilt Institute for Surgery and Engineering. We have lots of live demos that are lined up that I think you're going to really enjoy. And then the third announcement, remember you can do lunch basically anytime between 12 and 1, but you do not want to be late for coming back at 1 because we have our wonderful keynote speaker who's going to be starting right at 1 p.m., so you're not going to want to miss that. All right, coffee. Thank you, guys.
There is coffee in both poster sessions. So if you attend either one, there will be coffee there. Don't worry about it. But you should attend both.
pull this car back this way. I'm just going to run it up the leg there. Hey.
Okay. Yeah, okay. It does have a pointer, but they will not be able to see it on the webcast.
Oh, the pointer they don't show on the webcast.
Yeah, it's just a laser. I don't know which button, but
I see. So I should probably use the mouse then? Would the mouse show if I did that?
I think you can
No,
get
it
a
doesn't show.
highlighter somehow. I don't remember how.
So control something.
Yeah, there we go. Yes, they'll be able to see this.
But I have to do this. Is there a way to?
You may actually be able to use right control, but that's not helpful either. Yeah, no. slightly better.
Yeah.
Yeah, and the clicker is there.
So this doesn't show on the web, right?
Right. That's just
Okay.
the wizard.
All right. Thanks for doing this.
You have to sign.
All right, we'll get started. No, a little bit late, so tomorrow we'll start lunch earlier so you have the time to eat and come back. No, it's a great pleasure to introduce Professor Gustavo Rode as our first keynote speaker today. Professor Rode earned his master's degree in electrical engineering here at Vanderbilt, then a PhD in applied mathematics and scientific computation at the University of Maryland in 2005. After postdoctoral work at the NIH and at the Naval Research Laboratory, he joined the Department of Computational Biology at Carnegie Mellon as an assistant professor. In 2016, he moved to the University of Virginia as an associate professor in the Department of Biomedical Engineering and Electrical Engineering, where he is now a full professor. Dr. Rode is an imaging scientist whose work ranges from very theoretical to applied. He served as PI on numerous projects funded by NSF, NIH, and the Office of Naval Research, to name a few. He serves or has served as associate editor for leading journals such as the IEEE Transaction and Image Processing, IEEE Signal Letters and Sampling Theory, IEEE signal processing, letters and sampling theory, and data analysis, and he served as the 2021 ISB program co-chair. He holds a number of patents, and he's the founder and co-owner and CTO of a startup. Dr. Rode is an expert in optimal transport, which he has applied to problems such as automated analysis of digital pathology images or the early detection of osteoarthritis from pre-symptomatic cartilage texture maps. Now, today, he will educate us on how optimal transport could be used to enhance the performance of deep and other machine learning techniques for medical and biological application. Gustavo.
Yeah, thank you very much, Professor Dawant. Thank you also to the organizing committee, Professor Landman, Oguz, and Dawant. It's very nice to be back at Vanderbilt. I used to be a student here, also undergraduate and master students. In fact, I studied with Professor Dawant for a while. So I'm very thankful for the opportunity to speak with you. Thank you for the invitation. And so I always like to start with a slide to, it's always a hard thing to give enough credit to the people that have worked on this project with me for about 10 years or so. I'll name a few names, but it's unfair to others perhaps, but Wei Wang was one of the first to write papers with us. Sohail Kaluri, who might be present in the audience, as well as more recent graduate students that just graduated, Shifat, Hasnat, Yan, Shuang just graduated this year, as well as collaborators from Vanderbilt University itself, Professor Aldrobi, some of his students, and so on. And also like to mention that we have several openings to our lab, postdoctoral students as well as PhD students included. So, to set the stage to what we're talking about, I've seen several talks this morning and posters and etc. Many of us in this community are interested in learning problems of telling things apart, telling classes of data apart, not just from a robotics or automation point of view, but from a real scientific learning aspect, right? So for example, a question, is there a difference in brain morphology as far as gray matter is concerned between persons with high fitness index or low fitness index? Is there a difference in nuclear structure, nuclear morphology as far as chromatin can be imaged between cells that come from malignant tumors versus benign tumors, right? And as you can look at this, you can see by looking at this data, these questions are hard to come up with an answer by simple visual inspection, right? Doesn't mean necessarily that the answer is not there, but it may be hidden under some parameters that we'd like to discover. So the typical questions associated with problems like this are there differences between two or more classes, right? Are there differences there, scientifically reproducible differences, statistically significance, etc.? And if so, can we model them? Can we understand something, what the differences are? Can we come up with biological hypotheses that can lead us continuing going forward? So with that said, here are three topics that I would like to discuss today. Given this is a deep learning conference, of course, we'll start with hierarchical neural networks, and then we'll transition to transport mathematics and representations of image and signal data. And my point here is to show in the third item here how these representations can help you in deep learning and more generally in machine learning in general. So let's begin with hierarchical neural networks, right? So this is not a very new idea. It's actually quite old, depending on your time frame, but first few papers is maybe 1950s. Interesting that this paper is in psychological review, right? Not mathematics, not statistics, but psychological review. And the idea of the perceptron, right? Which we can summarize simply as a linear, so if X is your input data, and then you apply a matrix to X, you add an offset, a B, and then you take a sigmoid, a nonlinearity, and apply that, and you call that a perceptron, right? And of course, now this is just a notation where you swallow up this B here into the big matrix, and you call this matrix data, right? Just notation. And this is how people think of perceptrons. And then, of course, you use this as a basic Lego building block to build more complicated system, right? You put perceptrons all over this place, you put them into layers, and at the end you put perceptrons here to assign your output, right? One hot encoding is primarily the ways to do this. So if you just look at the perceptron by itself, it's very easy to notice the similarities between the perceptron and a linear classifier, right? If you look at the, let's think of images. The axis here is your input data, but it's a silly input data because your images only have 2 pixels, right? So it's a very toy-based problem. And this P of X here is your likelihood function, right? Your density for your data, for classes, which, of course, in a real machine learning problem is unknown, is what you would like to recover. And if you just look at the outputs produced by this perceptron, right? First, take out the nonlinearity. The outputs, this is just a projection, right? And those of us in medical imaging that work with image reconstruction can see the similarities between this projection and the so-called radon projection, right? Or the radon transform, which is essentially a projection of your data given a fixed axis, right? Of course, the nonlinearity here, sigma, is just to assign one class to 0, another class to 1, or one class to -1, another class to 1, but it's a made-up parameter. But this is simply the radon projection, and of course, you can take many radon projections, right? You can. Here is another likelihood function. You can take this projection, which seems to be very good at separating the stress classes, but the other projections maybe are less good. Particularly this one is not so good at separating these classes, right? And the whole business of fitting a perceptron or logistic regression is to find which projection is the best one to do the job at your data. And if you start looking at what happens if you nest these operations, you know, do nested perceptrons. Here is your first perceptron, which is essentially the equation for a plane. Right, the hyperplane, apply a sigmoid. You just and let's say in this hyperplane you look at the level set lines, right? And you can see here's another likelihood function. If you look at this hyperset, you see no separation between these classes. Well, you apply the nonlinearity. You just squeeze or separate these lines distance from one another a little bit, but no big deal. You can't really change the fundamentals of separating these classes. Well, you add another layer here. You start wiggling these lines around a little bit, right? You find that this isocontours now, these level sets are slightly wiggled, but still haven't done a good job. But by the time you add the third layer here, third perceptron on top of this business, you can start seeing that through optimization, you can start seeing some fits where you can start really separating this class. So in big summary, right? It's intuitive to think of a neural network as sort of like a different kind of high-dimensional polynomial, and your output are just your level sets of this polynomial, right? And the whole business is how do you fit this to data, very complicated, random initialization, different optimizations, stochastics, etc., right? But geometrically, this is what you're trying to do, which, you know, leads you to understand things in the following way, right? That why deep learning? The depth is concerned with first simplifying your data input, right? Of course, these matrices can have downsampling, they usually do, but it's not necessary from a geometric point of view. But the whole business of the first few layers is to turn your space, your input space, which was maybe hard to separate in its original data, to a space where now your last layer, which is again a linear classifier by definition, your last layer has to do a good job. So the job of this previous layers naturally have to be to do something to turn your problem that was difficult to solve, perhaps nonlinear, into something more convex, where machine learning and linear classifier is much simpler, right? Which leads to the topic of this presentation, is there another way to do this job, right? Meaning, can we come up with some other transformation, non-neural network, and this will be our transport representations, that allow you to achieve the same effect. And once the data is produced in this format, the simplified format, you can then apply your deep learning. You'll see even much simpler stuff than deep learning to solve certain problems. But of course, we're not going to attempt to solve every single problem under the sun. We'll specify when this should and when this shouldn't be used, which leads us to the transition. And before we begin this, we have to talk a little bit about what mass transport is. It's a very, very, very old idea, and it's really related to the concept of transportation, the intuitive notion of that word, right? Transport. So let's say if you have 2 piles of sand, right? This is pile 1, which is sand on the ground. Pile 2 is your castle that you would like to build. So you have to carry sand from one location to the other one. Carrying sand is a function that maps one space to the other one. I have to put some amount of sand present here to some amount of sand present there. That function is the one that tells me where to go. And of course, you know, if I take x from one to y to the other input, under the assumption that no mass is being created or destroyed during the process, right? If I have a certain amount of mass in one place, I have to have that total amount of mass in the other place correctly, right? So through simple mathematics, change of variables, and integration, you understand that you have to have the Jacobian on this transformation here, right? So the business of finding the mass for transport that rearranges one pile of sand, in our case, we're going to talk about pixel intensities onto another one, has to do with solving this equation. Of course, this equation is not unique. There are infinitely many F's that will do this job, and the whole business of optimal transport, originally introduced by Gaspar Monge, is to find the one that gives you the least effort, as quantified by the distance that you have to transport sand and the amount of sand that you have to transport from that distance, right? And if you minimize this, you obtain something called a Wasserstein distance. This was discovered later, which gives you a metric, right? But this is a constraint minimization problem. You have to get sand from one state to the other one in such a way that causes the least amount of work. Work not in traditional notion of physics, but here quantified by mass times distance squared. It's a very basic introduction to optimal transport. Those of us image processors or algorithmic people might be more familiar with the traveling salesman problem, which is a specialization or in some ways a generalization of that initial concept, right? But if you can just think of individual point masses here with 1/3 mass and 2/3 mass, right? And you have other configurations here you want to transport here. There are many options, so you can think of these transport matrices or transport plans, right? You can say, okay, mass at x1 goes to y1 entirely, or it could go to y2 or y3, and you can set up the same kind of cost minimization. This turns out to be linear programming. Those of you who in operation research are familiar with this. My proposal to you, one of the things I would like to impart on your brain before you depart this conference, is that this might be a good model to think about how to do image analysis. That observation doesn't come from us. Other people have of course, analyzed this. So, you know, let's imagine we have a distribution here, a signal. We can think of one, this signal. The same applies to an image, right? Applying that same equation that we had before, you can see how we can deform this image into any other image under very basic assumption of smoothness. And you know, if you're allowed to view your image as some kind of a density, which physically, from physics, you can actually, we claim that it is so, you can always find these transport maps, right? So this lets you rearrange intensities. Intensities in MRI are proportional oftentimes to proton density, right? So physically things match, right? But you can also do this with signals and so on. We have many of these transforms. So, you know, so you can translate functions, you can scale them, make them bigger, you can apply some non-rigid deformations, and pretty soon this starts looking like, you know, some people that work in medical imaging 10, 20 years ago, image registration was a big topic. I believe it still is in many, many respects, right? So, so we're going to use this model to rearrange pixels and see what can be done with them. And just a notation simplification, instead of writing this, I'm going to write like that, right? So this is the composition usually used in group theory, but that's the equation. Right, so let's use this mathematics to propose a model for image classes. Let's look at the canonical image classification problem. Perhaps one of the, I remember taking a class from Professor Dawant where this was part of the final project, and I think I messed it up, if I remember correctly, but recognize digits, right, from the MNIST. Right, and so I'm proposing here that you can use this transport mathematics to formulate this problem a little more carefully. Let's look at the class 1, digits 1, right? I'm going to imagine that I have a mathematical model. I'm going to write down a mathematical model for the set of all possible digit 1s that we can write. That model will consist of a template, a canonical form for digit 1, but observed under some random transportations or deformations, or ink smearings, if you'd like to think of that, right? And of course, these transportations will come from a specific subset. We can't have everything because if this subset is all possible functions of one-to-one, then we overlap the classes. That's not what we're going to do, so we're going to limit the set. But I'm writing this capital set here for a real set, right? And the elements of set are described here and can be seen as the transportation of a single template. Same model applied to class 2. Yes? Oh, you don't see the mouse. That's, oh, my bad. So I'm pointing with the mouse, and so I'm pointing to this set. Can you see this now? Okay, I have to click 2 buttons here to do this, so I'll give my best. Please remind me if I make a mistake. But here's set 1, right? So here's the template 1, right? And here's this template transported randomly by some random function chosen by a set of functions, one-to-one. And as I mentioned, we don't want to make this set infinite set of all one-to-one functions. I mean, they're all infinite sets, but they want to all possible one-to-one functions, because then we will overlap S1 and S2, which, you know, that's not a well-formed classification problem. So, and the point of this presentation is, if you take one thing home, is this problem stated this way has a closed form solution, right? That's one thing perhaps we can discuss in the end. Well, now I messed up because I have to use that. Okay. Of course, in a typical learning problem, situations aren't that simple, right? You're applying these things to actually learn, not just to automate. For example, what is the difference between nuclei from benign cancer cells and malignant cancer cells? Very difficult to figure out, right? So we still propose we have the same formulation, but we don't know what the templates are, and we don't know what the deformations are. This is your typical learning problem. This problem also has a closed form solution. Here's the outline of the solution, right? So we're going to discuss a new image representation method based on this transportation business. And you think of it as a transform. Like, we are engineers, we're familiar with Fourier transform, right? We know that certain problems are way easier to solve in transform domain, right? If you try to solve a convolution problem, probably you want to do in Fourier transform domain, it becomes it diagonalizes the operator, you can invert it very easily, right? Same thing here. We can solve that problem that I just described in this new transform domain. That's what it's built for. You apply your machine learning in this transform domain, and you can even gain something extra. You can invert this deformation and see your answers back in image space. The outline of the transform look very much like, you know, image registration. Those of us who work in image registration, medical image, here's registration in 2D, right? This is registration in 1D. But this is not registration. We're not going to register. We're going to transport. So it's not registration, but transportation. But the idea is the same. We choose a fixed reference for brains. It makes sense to choose a typical anatomical template for the brain, but we've done this with cells, images of faces, you know, many communication signals and so on. But you compute this transportation, this optimal transportation, which gives you a one-to-one mapping between any image input and a unique transportation map. This comes from optimal transport theory. That transport problem has a unique problem. So you can think of a transform between smooth probability distributions and diffeomorphisms. These maps are the diffeomorphisms. Just like you think of registering a brain to a template, you get the registration map, right? That's a diffeomorphism. That's not unique. You can't do mathematics with it very well, but with transportation you can. And that's it. That's the whole business of this transform. So if you take and you solve these problems, that problem that I just posed under some assumptions in this domain, you can solve it with linear classifiers, subspace methods, deep learning if you wish, but you don't have to. Here's a 1D version of the transform, very simple, right? So let's assume we're starting with PDFs for simplicity at the moment. We've relaxed this in subsequent papers, but let's assume that these are positive probability density functions. And let's consider this map such that the cumulative integrals between these two functions, S and S naught we're going to call our fixed reference. We find, you know, go up to S naught and we get an area, and we have to find what is the equivalent f of x at the S signal so that the areas are matched, right? So that's the graphical version of the problem. The integral version of the problem is written here. If you just write this with antiderivative notation, oh, yep, the mouse, thanks. What's here? Antiderivative notation, right? This is the integral of that. You see that you're just solving for a composition problem. If these densities are indeed positive, this map is increasing, and it admits a functional inverse, right? So this is the inverse function of S. And we call this f of S your transform, this f, this map. Just like you would call your registration map your transform. It's as simple as that. So keep going, right? So if we take for example, the uniform distribution, the chi function as your fixed reference, Then the integral of that is the identity in that domain, and your transform is just the inverse of your accumulation function of your signal. This is 1D, very simple stuff, right? And which means you have transform equations. You have forward transform, and you have inverse. Inverse, you just take the inverse of the inverse, gets you back to S, and you differentiate, gets back to S. Graphically, right? We're engineers, we like graphical, we like pictures. Here's your signal, here's the accumulation, right? Take the accumulation, and now take the inverse. You just flip the axis. Whatever was dependent variable, you call independent, and vice versa. Graphically, that's the transform in 1D. Why you do this? Because you gain properties. Like Fourier transform has a translation property, this transform also has a translation property, which is different, but it's called a translation property. If I translate a signal in transform domain, I add, right? Translation becomes addition. If I scale a signal here, by composition here, that whatever composition comes out of that thing. More generally, we write this composition problem, right? Which means any shifts in the dependent variable, Lagrangian representations in PDE parlance, become shifts in the dependent variable. Independent variable shifts become shifts in dependent variable, or Eulerian representations in PDE language. What does that buy you? If you look at the data geometry of just a set of functions composed of a single function, a template, and all of its translations, you can understand the set is not a linear structure, right? You take the convex combination of this function, you don't get a one bump function, you don't get a Gaussian, right? So if you just do PCA of this set, you see that this is a nonlinear structure right away, right? PCA with 3 components. You do this in transform domain, you get a perfectly linear set. With this kind of intuitions, we can form some solutions to that classification problem I just mentioned, right? So if you observe class P here to be composed of a template observed under all possible translations, class Q is another template, 2 bumps under all possible translations, you understand that to solve this, you may need a deep learning, right? Several layers in the neural network to do this job well. But if you do this in transform domain, in fact, you can even guess a classifier here, right? And you would be able to solve this correctly. This kind of representation leads us to formulate this problem with many interesting theorems. Here's one version that says, if the classes are formed the way that we just talked about, meaning a template observed under some random compositions, under random transportations, and C is a group, right? Then this, in theorem, the theorem says that in this transport transform domain that I just described, these sets will be convex and thus linearly separable if this group is convex, right? So there's several versions of this kind of theorems that we've published throughout the years. Other people have been publishing similar versions, similar work. We can extend this from 1D to multiple dimensions easily with the Radon transform, right? So if you take an image, take the Radon transform, and take the projections, each projection can be applied to CDT business, and you have what we call the Radon cumulative distribution transform, right? And more generally, you can apply the optimal transport theory. This slide may be difficult for some of us to visualize that. I'm not familiar with optimal transport, but this has relations to an earlier paper of ours called the linearized optimal transport. All of these transforms are some version of this, where we take a reference function, right? We take a reference image, your reference brain, your anatomical average atlas, and we map all of these to, transportation maps to all this reference, and we take these maps, which are uniquely characterized as the gradient of convex function, to be our transform. So we can view this as projections. These are invertible projections. So this is like, your exponential map, inverse exponential map, kind of from differential geometry, right? So there's some mathematics behind this. So in summary, you have this new kind of transforms that we call, there are several versions, 1D, 2D, 3D, for densities, for sign densities, and so on, that help you linearize or make your machine learning problems easier. What they do, in fact, if you look at the Euclidean geodesics, right, between 2 images here and here, you see that the Euclidean geodesics are really not appropriate for a lot of image processing problems. They produce a mixture model, but that's not really what goes on in many image problems. If you take the geodesics in our transport space, you can see that pixel intensities are moved around, which is what people are trying to achieve oftentimes when they're doing registration. So how does this solve the supervised learning problem we just discussed? If you assume the data comes indeed from these models, right, where your templates are unknown, the deformation models are unknown, but they satisfy that the only assumption is that these form a group, a convex group, then And if we want to find the class of a set testing sample, all you have to do is take the transform of your training data and your testing sample, just apply a near subspace method or a linear classifier method there. You've solved the problem, mathematically guaranteed, so long as you have enough training data to characterize the sets, these subspaces well enough. If you apply this and you compare to deep learning literature, right, you'll see applied to Chinese characters, MNIST, fine MNIST. This is an optical communications data set, sign language data set, brain MRIs, and you compare to shallow learning, deep learning, and you look at accuracy on the test set, average accuracy of test set as a function of the number of training data in the training sample, and you repeat this experience many times, you can see that there's some benefits of using this transportation primarily because you can solve the same problem with much fewer data. You still get the same, or sometimes better, sometimes slightly worse accuracy as deep learning in the very high end of training samples. But you get other advantages as well, auto-distribution performance, right? So for example, take affine MNIST, but you only train with plus or minus 2 pixel translations, but you test with 10 pixel translation. Deep learning, in a way, deep learning doesn't learn, it memorizes, right? It's different. So if you do that, you can see the performance of deep learning can be quickly degraded. As opposed to these methods, they maintain the performance. Computational complexity, if you look at test accuracy that you obtain and the number of floating point operations that you need to use for training, for example, you can see that these methods are 4 to 5 orders, not times, orders of magnitude cheaper to compute. The downside is there are limitations to this. This doesn't solve every single machine learning problem out there. It solves problems that conform to this model. So for example, if you take ImageNet or CIFAR10 and you try to apply this, this doesn't work. Why? The data is unsegmented. So even though some objects in there may conform to this model, the background doesn't. So it has trouble with that. So in fact, I wouldn't use it for that, and you can see the performance is nowhere near as good as deep learning. Which leads us to the last part of this thing. What does it have to do with medical imaging, right? Let's apply this to some problems and see what we can gain. And here, the nice thing, the nice connection is that if you think about things, you know, ask yourself, what goes on in a cell? What goes on in the brain? What goes on in the tissue? And we can play some movies to inform our intuition, right? So here's a movie of actin. Actin is a protein that forms filaments inside the cell. This is the same cell image over time. This is the same brain image over time from birth to 48 months. And then you ask a mathematician, let's say, if, you know, what are the equations that describe this thing? What's going on? You know, the natural answer here would be, well, there are two things going. So if I focus on a particular pixel here, the red pixel, okay? And I try to come up with a differential equation, di dt, for di as a function x, y, t, right? What are the possible things that could be affecting the increase in intensity at that voxel or the decrease in intensity in the particular voxel? So you know, even Homer Simpson could come up with this and say, well, there are two things. Tissue is moving in or out of that, material is moving in or out of that voxel. That's one, we'll call this flux, that velocity, right, which is the intensity times the velocity vector at that point. Or material can be created or destroyed. There are only these two possible things, right? And of course, in medical imaging, typically you don't have calibrated units, so you can't quantify if mass was created or destroyed in that typical MR image, right? Some very carefully calibrated experiments you can, but in generally speaking, these machine learning problems you have arbitrary units for intensity, right? You don't have absolute intensities. So we don't have this term, but we have the other ones. And it turns out that these other ones, this is so-called the dynamic formulation of optimal transport, right? So it's optimal transport is what a physicist, so if you're given two data points, this image, and you ask a person to make a reasonable conjecture for how the cell could have gone from this to this or vice versa, one option would be through, say, well, the least energy or the least action, right? This is a very, very well-used concept in physics. And that's exactly optimal transport. It's a guess. It fills in the spots in your data set. You only have sample data, but if you want to make a reasonable guess of what goes on between two samples, I argue that optimal transport is at least a good starting point, right? And you know, there's famous theory from around 2000 that links this to optimal transport formulations to exactly this least action guess in physics. So go back to to our business of image analysis, we created what we call the transport-based morphometry framework. Very similar to the registration framework that you're used to, right? Here's your data set, here's your template, your atlas, so on. You quote-unquote register, or you transport your data, compute these unique transport maps. You then do all your machine learning in these transport maps. And you have varieties. You can do deep learning, you can do exploratory analysis with PCA, you can do LDA, canonical correlation analysis if you want to correlate to some independent variables, so on. And then you can even invert and obtain whatever model you estimated in transport space back, because this has forward and inverse equations like we just discussed, right? So here's the situation. You have your signal space where things may be hard to compute, hard to discern. You linearize them with this approach. You do your machine learning. Here's our yellow line, and then you invert the line again to see things in image space. So let's look at some applications. Nuclear structure in cancer, right? There's some papers here that look at histopathology. This image is very large, right? So this can be easily a couple 100,000 by a couple 100,000. You zoom in, you have very high detail. From this, you can extract several thousand, if not million, of nuclei images, all of these looking like this, right? Each of them a 256 by 256 image, right? If you want to do exploratory analysis on this, here's your PCA in transport space, right? So, right, if you look, the data here is very disorganized. You ask what goes on, what are the main modes of variation? Well, do your PCA here, obtain your expansion in transform space, but then apply the inverse formula to obtain the answers back. And then you visualize the features here. This is one feature. Clearly size is what's going on. Clearly elongation going on. Here's, a chromatin displacement from center to the periphery, right? Here's some blob to the left, to the right. And if you look at all of them, they start looking like spherical harmonics, right? But you can organize your data, allow it to visually explore what the data is. If you want to solve discrimination problems, right? Learning this versus that and learning what the differences are, same thing. You take your data in original space, transform it, fit your linear classifier here, and then since this is an invertible transform, you can go to any point on this line, whether this point was sampled, whether there was an image corresponding to this point in your original data set or not. It's not a problem. This is a mathematical formula. You can invert any point here back to image space, and this is your inverted classifier. Your actual classifier being visualized in image space, and it tells you, oh yeah, chromatin organization from center to the periphery is the most discriminating feature between these cancer types. And then pathologists can go to this, oh yeah, this makes sense because cancer is a phenomenon of fast reproduction in cells, right? For cells to reproduce, they have to divide. Before they divide, the chromatin has to be spread and open during the nucleus. Things start to make sense. You can visualize, interpret your classifier. It's not an opaque thing. Going on to tissues, right? So this student, Shinjini Kundu, did wonderful work to look at cartilage, and her objective was to see if she could predict the onset of osteoarthritis symptoms in the future. Right? So you take an image now, and 3 years from now, you may develop symptoms of osteoarthritis or not. Right? The question is, in the image of your cartilage, T2 image that cartilage that took now, is there information to predict? And she's tried to solve this problem. She used a data set from collaborators with NIH. And right, so here the progressives, the ones that started developing osteoarthritis, here the ones that didn't. Right? This is T2 heat maps. And you can solve these problems in transport space, and you can see the difference. You gain quite a bit of accuracy in respect to not using transports. Whatever machine learning, if you do in transport space, you usually get a substantial bump in accuracies. And you can even invert these classifiers and start obtaining, tissue regions where the transport of T2 information tells you where to look for abnormal things, right? You start interpreting things. Brain imaging, similar. Here is a study with collaborators from University of Pittsburgh. This is also done by Shinjini Kundu, who's now at Johns Hopkins, of trying to discern differences in gray matter tissue densities between people that exercise a lot and people that couch potatoes, like myself, right? And does that have an effect in your brain in the long term, right? And so what she did is she tried to actually correlate this with aging, right? So aging has also an effect on your brain. And if you look at this transport-based morphometry analysis to see what it tells you with respect to aging, right? It says that there is a 0.78 millimeter shift in gray matter distribution as far as transport pushing gray matter on average for every 10 year of age increase. This is canonical relational analysis applied in transport space, pure and simple. Similar if with the decrease in milliliters per kilogram per minute, there is a shift, a similar shift, 0.73 of gray matter distribution, also with low exercise, right? So, and you can visualize and you can look at the regions to say, here's the regions of transport shift in aging, right? You can see some definite areas where there's more shift in gray matter distribution, and if you look at cardiodisperse, they're the same regions, right? So she was able to postulate, to propose that the shifts in gray matter distribution, as far as exercise is concerned, correlate very well with shifts in gray matter distribution as far as aging is concerned, right? So this kind of studies with the ability to invert your classifiers, they're not opaque, right? This deep learning is sometimes problematic because you can't quite understand what it's doing. Here you can know exactly what it's doing. Take-home messages, right? So a lot of stuff, a lot of new things. Let's summarize them, be a little bit more careful, right? So first, take-home message. This type of mathematical problem has a closed form solution. You don't need to minimize, do gradient descent, stochastic sampling, blah, 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 right? If your data can be modeled the following way, that is composed of one template or more than one templates per class. This also works. We have extended this. But you don't observe the template, but you observe a version of this template. And this version is some kind of transportation of the original template. Translation is a transportation. Scaling is a non-rigid deformations are a transportation. This is what I'm talking about. And if these confound groups have certain basic assumptions, then if you take this data to this transform space, you create convex sets for which you can come up with closed form solutions under some assumptions. Let's take home message from tomorrow, which gives you an option, right? So in deep learning, we discussed that what's deep learning? Why deep, right? Because the final layer is a linear classifier, so the initial layers must, if deep learning is to work, the initial layers must do the following job, which is convexify this data, right? Through the Hahn-Banach theorem, you know that if the data is convex, there will always be a linear classifier, right? So meaning you can create an if and only if version of that theorem by saying the convex hull of the data. If the convex hull of your data is, then it's linear classifier, right? So the only way for deep learning to work is if these initial layers do that job. For these problems that we just discussed, you can actually do the job of the initial layers using these transport representations, right? For those problems only, not for everything under the sun. I'm not talking about distinguishing a bicycle from a building, right, with backgrounds. That's a different story. But for template, things that have to do with something canonical template, observing deformation of templates, cells, tissues, and organs, I try to make an argument that physics supports this notion. And you gain some more, right? You gain the ability to observe. This is a transform, like a Fourier transform. You can invert it. You obtain the ability to visualize whatever model you obtain in transform space. You can visualize it, invert it back, and visualize it in image space to start understanding some hypothesis for your data. Summary, right? So these transformations allow you to move peaks around, which is, you know, the main reason why imaging problems are hard to solve, these problems of telling things apart, is because things move around, right? That's the confound that if every brain was always the same, every face was always the same, problems would be easy, right? But that's not the case. Things move around. And this is what this is meant to do. There's software for this. If you just type this name, PyTranskit, on Google, you come up with a Python package where we're putting all the papers, and we do, the functions are there. Each paper comes with a notebook. You can reproduce all these papers. And again, thank you to the many students and collaborators that have helped us put this out there. And thank you for listening.
Hello, Raza Marinescu from UC Santa Cruz. Thank you so much for your talk. It was phenomenal. Couple questions. So it wasn't clear to me, but do you always have to know the latent space Like, in the sense, do you have to always have a fixed template that you assume a priori, or can you also optimize the template from which you do the transportations?
Good question. So let me go back to this. Maybe this is a good slice, right? So you don't have to know what the template is. If by know you mean do you have to estimate it, the answer is no, right? Meaning that all of this, the algorithm is actually here in graphical form. It's very, very simple to compute. Only 2 steps. I think here, yeah. Take your data, take the transform.
So that transform space, do you have to know it a priori, like with those kind of lines, or is that also optimized at how those latent points
Correct. So
being
once, let's say you have, this is a sign language data set that we use. And I don't know sign language, so I can't make the specific example, right? But you have sign 1, you have your training data for sign 1. You just take the transform, and then you have options there. You can use that data. You still have a machine learning problem. I'm not proposing any substitute machine learning here. Machine learning is there. What happened now is that if your data was, if the physics that describes how the data was generated conforms to this equation, then your data in transform space will belong to a convex set. And under certain assumptions, you can model that very simply with a linear subspace. Just fit a subspace with PCA, extract an orthogonal basis there, and that's your subspace for that class. Take the transform for another class, fit your subspace there, and that's your subspace for class 2, right? And then for a test sample, all you say, well, just measure the distance to the subspace. If you have actually orthogonal bases, it's easy to take the projection, and you just take the closest subspace. That's one way to solve it. Another way to solve it, you can make the observation, well, these are convex sets, which means under enough samples, I can even fit a linear classifier. Deep learning should be an overkill here, but you're also welcome to apply it, right? So this is a mathematical point. It's not an algorithm. But if your data comes from a model that says like this, and here we used only one template. In fact, each class can be modeled by more than one template as well. Yeah. But if the equations that describe how your data was generated conform to this, your solution is very simple. You have some machine learning method you like, great, keep it. You will have much more success with it if you apply that machine learning method in this transform space. That's the message. But you don't have to know, or you don't have to estimate that template for that class. No. And you don't have to estimate any of these deformations G. Right? You could, but the algorithm we're suggesting doesn't require. Yeah. There's a function here we call CDT, and you would use it just like you call the FFT. Call FFT, apply machine learning. Call CDT, apply machine learning. That's all you need to do. You don't need to estimate this versus that.
So in a medical imaging setting, say if you don't know the template, so can you still estimate it with this framework? And
yes.
Also the transport functions?
So there's a difference in nomenclature here that I use the template and the reference. Let me find a slide. Right. Wait, I don't know where it went. There's one slide here. Maybe I can find it quicker if I do this. Right, there's a reference which is different from the template here, right? So this is a good one. Right, so to compute this, yeah, it's showing, oh here, not showing too. So to compute this transform, you must use a reference. And here it makes sense to use an anatomical atlas for reference. For example, you wouldn't use an image of a face here because it's a brain problem, it's not a face problem, right? Yeah. But you use an image of a anatomical reference. Yeah. That's a difference than the template that generates class 1 versus class 2, right? So this one, you would want to use some average atlas to obtain that. But if you're trying to learn the difference, later on we try to learn differences between class 1 and class 2, it's not like I have to estimate a template for this class and estimate a template for that class. That's not required. All is required that is your reference at the beginning and the registration or transportation to that reference. again, this doesn't guarantee that your problem will be solved better in this transform space. But if the data that if the laws that generated this brain conform to those equations, then this will solve. But we don't know enough of the anatomy and biophysics to make that claim just yet. Although I would venture that starting from that continuity type equation, transportation type equation, is closer to, I don't know, it's closer of a model to the real truth than deep learning would be, than compressed sensing would be, than SIFT features would be, right? I think we're closer there, but we cannot say that we have the right biophysics.
Yeah. Makes sense. I'll follow up afterwards. Thank you.
Sure.
Yeah.
Great talk. So it sounds like when you're using these transport-based methods, if you're doing like a brain problem, you get a model for the brain problem. And if you're doing a pancreas problem, you would have a model for the pancreas. We know in deep learning, sometimes you can train a model here, and you can fine-tune it maybe over here if the problem is related. Does that type of approach work with these transport-based methods?
I don't know. In the context of this transport-based morphometry, where you're observing some kind of anatomy and under some random transportation or some random modifications, I would have a hard time coming up with a justification to say, hey, what can a liver teach us in that space? I don't know that you would gain anything from doing that. Now, we have a lot more image analysis and signal analysis work that using these transport methods that we're not describing here. One of them is creating metrics that are invariant to illuminations and other intensity transformation. That you can transfer, what did you learn from illumination here, illumination there. But I tend, if I may make a suggestion, like I would seek for these kinds of relationships if they make sense, right? I don't know what the liver morphology would have, how can it inform brain morphology studies, right? To me, I'm not saying that it doesn't make sense, but right now I don't know the sense that makes. And I wouldn't push that connection just for the sake of pushing it or just because some other people in deep learning have pushed it, right? I would ask a question, what can liver morphology, how can that inform what we can discover in brain morphology? There may be a link. I just don't know that there is.
Okay, thank you.
Thank you for your talk. So I think on your slides you showed that your methods didn't extend as well to natural image data sets like CFR10 and ImageNet. And I guess I was just curious, and you mentioned that may be because of the presence of background. I was curious if you thought it would be a worthwhile endeavor to try to change the problem to better fit the assumptions you make and potentially get better performance on that type of data set, or if it's just kind of an entirely different scenario that it couldn't extend very well to.
It's a great question, right? So the reasons, why, or can we provide the necessary extensions to these formulations so that it can be successful in more and more general problems like classify an unsegmented data set like ImageNet? It's a great question. We ask ourselves these kind of questions every day. It's not clear to me how to do that yet. We have some papers where we've begun doing this, but looking at intensity metrics, right? So in some way, one way to think of this business that we have presented here, people in signal processing, they call phase modulation versus, where did it go? Sorry, I'm making you dizzy, aren't I? Mm-hmm. Yeah, sorry, I'll stop that real soon. Right? They call converting phase modulations to amplitude modulations, right? So what we're saying here, the message is, if your data set is confusing because there are transportations going on, changes in the independent variable, we can convert them to changes in dependent variable. So the path that we're thinking of right now to answer your question, but the answer is we don't know, we're working towards this direction. But the path we're taking there is some data sets will have both. They will have translational confounds, Lagrangian confounds, so to speak, deformations, and they will also have intensity variations. So a general problem would, a more general problem than the one we're looking at would include both formulations. And there are ways to solve for both of these, and we're beginning to put them together. That still doesn't address the background issues, which is even another completely different, even higher level of complexity, right? But little by little. So I think this kind of work begins addressing these phase modulations that you see in data. You can flip it around and apply it to intensity modulations, and you can try to combine. We're beginning to do that. The adding of the background on top of it is not like, you know, one thing at a time. Like we, things are hard enough to do one at a time. We're going there, but it's a great question. The honest answer is we don't know, but it would be nice if we could come up with something like that at the end.
Okay, great. Thank you.
Great talk, many thanks. I was wondering if you can solve in the same setup of transport function the following problem. So sticking to your setup with brain MRs, let's imagine we have a set S1 of healthy brains, and you also have your reference, which could be the atlas of this distribution. And then is it possible to find a set of transport functions that kind of describe these data sets, but they don't overlap with any potentially unknown sets? So how can you constrain that these functions really describe just the distribution that you have, S1, under the condition when you don't know anything about S2 or S3 or whatever?
Great question. Very, very nice question. The answer is, again, I don't know. But we have thought and we have some kind of direction that we're pursuing that may address some of this question. And in fact, this, like, you know, it would be very tempting, right? For example, let's say somebody just gives you one sample per class, right? And then you make some reasonable physical assumptions and says, I don't need more training data. I can solve for this classification with just the mathematics, just the assumptions, with just one sample per class, and I can solve for all the testing sample, right? And if you can take that one set into this formulation, where did it go? Right, and to this formulation, augment that set mathematically. You know, people in deep learning may call this data augmentation. Here we call it mathematical augmentation. It's a made-up word, right? But like we can formulate that set with an equation that, and we can increase it as much as we would like, and the constraint would be, as you said, that the two classes cannot overlap, because if they do overlap, we've broken the problem, right? We've broken our ability to solve the problem. So we call this mathematical enrichment of these subspaces in transform domains, and we have papers towards that, meaning we can solve some of these problems with very ridiculously few data samples, as long as we make the necessary assumptions that, you know, your problem needs to be translation invariant, scale invariant, rotation invariant, affine transformation invariant, small deformation invariant. We keep enriching them up until the limit is the classes cannot overlap. If you start overlapping the classes, again, you've broken the rule, right? But that would be the path, I think, to provide a solution. If I understood your question correctly, I may have misunderstood it.
I think we're halfway there, so many thanks for the answer. And what happens if you don't know the class? If it's a new disease you've never seen before, so you cannot check this overlap?
Yeah, if it's, you know,
so you have no samples.
then I think you are in to use a machine learning language, I think you're in an unsupervised setting, right? Because you may have some training sets that describe some classes, but you may be missing some classes. And at that point, your classification problem is maybe, you know, you're trying to make a detector of something out of distribution, right? And that potentially you could do again, but you would have to be very confident on your training sets or on your ability to augment your training sets with the correct deformations, right? The beauty of this work is if these deformations are encoded mathematically, then you're sure to capture them. It doesn't depend on this training data or this training data point, right? And that means if your new point doesn't conform to this, then it's definitely a new class, right? So it provides you a formulation to begin thinking and addressing those questions, right? I think if you went the pure deep learning route, you'd be sort of lost as far as to some of this question, right? So.
Yeah, many thanks. Have you tried some unsupervised approaches for yours?
Not to be frank, not quite. I mean, people in the lab are trying different things every day, but we haven't pushed for like solving an MNIST unsupervised problem. I think it would be easier, but we haven't really try to do like a completely unsupervised solution to MNIST or any of these other data sets, but I think it's an interesting thing to do.
Okay, thanks a lot.
Thank you for a very insightful talk. I was just wondering, so on one slide you showed, okay, the equation where the intensity distribution is related to two potential terms, right? Tissue moving around or tissue being created and destroyed.
Right.
And you said, okay, that last part is typically not there, but the example you showed, like the brain from like month 0 to month 48, is specifically one where I would say tissue is being created. So how would that alter the modeling?
Yeah, great question. So, you know, this transportation, this idea of, it appears there before here, okay. I think this is the slide you were mentioning, yes. Right? So, absolutely, like, you know, this term definitely is here, right? And what I'm saying, our modeling doesn't include it, right? People have begun, starting from our point, and included formulations of optimal with creation and destruction of mass under reasonable assumptions, right? Somebody sitting next to you is writing papers like that at the moment, right? So you start from an equation like this and propose, you still have, you know, like really only God would know what that other row term would really is, right? So you still have to make some reasonable assumptions there, but starting from an equation like this, from this construction, you can create this transportation matrix which are not necessarily they're not constrained to be mass preserving. Mass preservation is not a requirement into this extension of the framework as it is in the work that we're doing here. We also have our own work that extends this beyond, right? So absolutely, there's extension to use this linearized optimal transport matrix the same way as we're doing here, but now accounting for the fact that different signals, but I argue, you know, I just throw a word of caution there, right? Do you have information about kilograms in a T2 image of the brain? And the answer typically is no, right? So people that are doing brain morphometry studies, the normalization like this that they all integrate to one is typically done there already, right? But absolutely, specifically in cell imaging, there are some very carefully tailored experiments where you can actually observe fluorescence is linearly proportional to the amount of mass there, at least within the same image. You can trust that, you know, if you observe an intensity that's twice as large as the neighboring pixel, there's twice the mass, roughly speaking, then of mass there. So there are some situations where that is present, and for that there is, optimal transportation approaches which are relaxing the constraint of mass preservation. They're coming up as we speak.
Okay. Thank you.
Last question. Thank you for your great talk. How can we use this transformation-based method for dense prediction problem like image segmentation as its demand pixel level segmentation?
Yeah, so, you know, I propose everything that you're seeing here. We have more papers that do things like you're saying. I propose this canonical problem of telling, you know, one class versus another, right? So if you, this is canonical problem, machine learning, this versus that, right? This framework is essentially a new mathematical method for measuring distances between images, right? This Wasserstein distances, transport distances are really meaningful because they measure quantities that you know are in imaging problems, right? And they're better than Euclidean metrics. So we have other papers, not discussed here obviously, where we use these metrics to perform things like image reconstruction, right? Filtering, detection, estimation, all your traditional signal processing methods. We haven't produced a paper for image segmentation, but we have for signal estimation, which is something related, right? So the idea is to first recognize that these are different metrics. Okay. Everything that you do in image, I mean, it's too general language, right? But a lot of things that you do in image processing begin by you ascertaining what metric to use. And typically that's the Euclidean metric, right? And if you're going to play with Wasserstein type distances, it's a good idea. This transformation that we give to you is a way to speed that up, to simplify that, right? And so you can use that. We can construct, I can share with you if you come to me, some papers where we did this signal estimation problems, image estimation problems. They're not quite segmentation yet, but they're close.
Okay, thank you so much.
Thank you.
Thank you. Thank you to the speaker for the presentation, for the lively discussion. And
thank you.
So now we'll be transitioning to our next oral session, but a reminder to all the speakers, please, for everyone's listening benefit and for the benefit of our wonderful AV team, speak directly into the mic. And also, this is being webcast, so if you do not speak into the mic, the internet cannot hear you, so people will be confused and won't be able to understand. So if you're going to speak for a question, please speak directly into your microphones, and otherwise you just need a normal speaking voice. No need to yell. Yeah. Now I'll awkwardly pull up slides while you look at me. Oh. Yes, well, this is our missing one. Apologies.
All right, so we'll get started with oral session 2. I'm Jack Noble from Vanderbilt University.
I'm Yang Kai Huo from Vanderbilt University.
And our first paper in this session is going to be Generalizing Unsupervised Anomaly Detection Towards Unbiased Pathology Screening. I'll let the speaker introduce himself.
Yeah, many things. It's tough to follow the great keynote speaker, but yeah, I did my best. I also want to thank to my doctoral parents, Julia Schnabel and Daniel Rückert, and to our clinical collaborator, Benedikt Wissler, for the support. I'm Cosmin, and I'm going to guide you today to some of the challenges that we face with anomaly detection and one possible solution to address these challenges and to bring these networks closer to clinical acceptance. So let's start off by first explaining what we actually learn. So we don't do anomaly detection directly, but our goal is to learn the normality. So the question is then, how does a healthy brain or a healthy chest, for instance, looks like? And this is quite an abstract goal, but what we do is, for instance, in reconstruction-based methods, we try to extract some features from this distribution of healthy. In this case of chest X-rays, they could be the shape of the lungs, the intensity of the lungs, or the size. And the aim of this is then when we get a new sample from the same distribution as the one that we trained on, is then to reconstruct it from the information bottleneck that we extracted with minimal error. And once we get a sample that's out of distribution, you can imagine what should happen ideally. So the networks are constrained to kind of extract the same features that was trained on. So in this case, Angelina Jolie would be transported to a chest X-ray manifold, and that would make it easy to find her as an anomaly. So this is the main story that we have. It's a very nice story, very appealing, but in practice, it's very difficult. So it has some really strong assumptions, and in order to methods to do that, you really have to be careful how you design them. So if you look at a recent review paper, we have here on the left a brain MR slice with multiple sclerosis lesions, and on the bottom the ground truth annotations. So what you see from the different methods that follow here, the different reconstructions, you kind of classify the methods into two big groups. You have these methods that kind of do a blurry reconstruction of the input scan, but still can find the anomaly quite well. And you have methods that do accurate reconstructions, but actually copy the anomaly. So they more or less learn just identity function of the input, which is not really helpful when you do then anomaly detection and downstream task. So then you might ask, why do we care if it's blurry, if we can still find the anomalies? Well, we can find anomalies in this case because they are kind of hyper intense, so they pop out of the image. But it turns out we can do just thresholding the input and we get similar performance or even better than deep learning methods. This was work done by Felix Meissen. Or if we switch to other domains where the hyperintensities are not just to do pathology, but maybe you have the skull, which is really bright, or also other type of anomalies, these methods would really result in large false positive detections. And this is then, of course, not useful in a clinical practice, since you would have a lot of post-positive detection that would not help a clinician in any way. And the other type of methods would just basically copy all the anomalies and wouldn't find any problems in these images that I'm showing here. Now, if you're turning to more recent methods, there are these denoising autoencoders that we also heard about today. They do a different task. So what they try is to have some noise in the training and then remove this noise, with the hope that when you do inference on some kind of anomaly images, the network would remove them and then kind of detect them. This works very well as long as the anomaly is in the same distribution as the training noise. So if you use coarse noise for training and the anomaly kind of resembles the same noise, it works. But as long as you shift from this distribution of the noise, then it starts to behave really weird. This is a congenital anomaly case where you see the posterior of the ventricles enlarged. The network noticed something weird with the image, but kind of inpainted over the ventricle, but it doesn't really reproduce a pseudo-healthy version of it. And if you go to purely structural anomalies, like for instance these enlarged ventricles, which could be an indication of Alzheimer's, this network completely fails. So it will not find anything wrong with this image, because it's not similar or it's not part of the distribution it was trained on. So we try to address this and bring up networks that can detect multiple types of anomalies, so not specific bias to detect any hyperintensities or not introduce any supervision in the training set. So for this, we use an autoencoder-based model. We start by using a variational autoencoder, because we'd still like our latent space to be smooth and to regularize it well. Of course, this would lead to kind of blurry reconstructions that you saw before. So in order to mitigate that, we add an adversarial loss. So this adversarial loss, you know from guns. It's kind of a game they play. We have these fake and real images. There's usually a discriminator. And then this improves the reconstruction of the images. In our case, we use an introspective loss, meaning we don't have an external discriminator. But what we do, we have a play or a game between the encoder and decoder. The encoder tries to fool the decoder decoder tries to fool the encoder, and they play this game to produce really nice looking images. With the problem that the images that are produced, they are nice, they are detailed, but they are hallucinated, so they differ a lot from the input. And then again, when you do the difference, you would have false positives just because it's another brain. So to mitigate this, we introduce in this paper this reversed loss. The main idea or the gist of this reversed loss is that we want to enforce that the embeddings of the inputs, it's very similar to the embeddings of the reconstructed inputs, meaning that we should have the same features or structure in the input as in the reconstruction. And with this, we want to enforce that the input reconstruction coherence, it's really there. Once we have this input, X, it's a pathological input, and also our pseudo-healthy reconstruction, there's still the question how we compute these anomaly maps. So usually what is done, it's you just do an absolute difference between the images, which is not great. I mean, even if you have small shifts in the reconstructions, this would lead to high responses in the anomaly map. And if you have subtle anomalies, it will lead to low responses in the anomaly map because it's very intensity-based or intensity-driven. So we try to mitigate this in this paper, but this is a whole topic on itself, by using perceptual maps. So we augment these pixel-wise anomaly maps with some perceptual maps. The perceptual maps are much more similar to the human perception. So if there's a shift, a slightly shift, the perceptual map wouldn't really respond to that, but it would respond to really visible differences in the input and the reconstruction. But of course, since it comes from deep features, it's quite coarse if you upsample it to the image space, and then we combine it with this pixel-wise loss to get really precise localization of pathology in the regions which look perceptually unsimilar or unhealthy. In order to evaluate this, we needed to find kind of another data set, since most of the data sets are really focused on one disease. You have BRATS, which is tumors, you have MS lesions, and also mostly are flare and hyperintense. And I found this fast MRI data set, so it's originally done for another application. It's a reconstruction from K-space, but there's a group which annotated about 1,000 samples, so we have 30 local anomalies and different anomalies. We have everything from resections, mass, intraventricular substance, even this atrophy like enlarged ventricles. We wanted to see how the methods perform on that. And the first question we ask is, can we do pseudo-healthy reconstruction? So given a healthy image, we want to augment it in some way to some synthetic anomalies, and then try to see if the methods can remove this anomaly and reverse it to the original healthy brain. As you see, you can notice kind of the same behavior. There are some methods that just copy the anomaly, and then they couldn't detect it. or the variation autoencoder, which produces these blurry results in the reconstruction, which also leads in high false positives around the skull and everyone else. The denoising autoencoder, interestingly, also completely fails to find this anomaly, simply because it's not just an intensity-based anomaly. It does some smoothing here in the brain region, so it kind of tries to adapt the synthetic anomaly to the image, but still fails to detect it. And as you can notice, our reconstruction is quite close to the ground truth, so it does a pretty good job in doing this pseudo-healthy reconstruction, and it can also isolate the anomaly quite well. And we tried it on this data set that I mentioned before to check two different things. So one is the global detection. The data set has also some global anomalies. So it's anomalies where you cannot pinpoint on the brain what went wrong, but it's more like a global a chronic disease that was going on. You have chronic stroke, or global artifacts that are usually due to motion in the acquisition time. And we achieved here a clear improvement compared to state of the art. But what's more important, when evaluated on these local pathologies that I mentioned before, so we have these 13 different classes of anomalies, we managed to improve the detection of these lesions to 86%. This is important because if you have it in a clinical setting, for instance, when you want to do screening, you want to make sure that you detect most of the anomalies, or ideally all of the anomalies, but also with low false positives. Otherwise, you just refer all scans to the pathologist and you wouldn't win any time. So we mentioned to really increase the recall to 86% while also increasing the accuracy. So it's not just a trick where we have low accuracy but high recall. We increase both the recall and the accuracy. And if you look at the distribution of the diseases, we do quite well on a range of different pathologies. And especially if you look at the structural anomalies that I was mentioning before, we have 100% recall. So we find all cases of these enlarged ventricles with quite high or quite confident accuracy, about 80%. This is a qualitative example. So some diseases that I showed earlier, resection, enlarged ventricles. So the first row would show these inputs with red boxes annotated by experts. The second row would show these pseudo-healthy reconstructions of our method. So this is, if you want an orthogonal projection to a healthy manifold, this is a bit strong. So but this is the idea, to have the image of what would have the patient look like if we don't have this disease. And then we can do the difference, and we get these anomaly maps on the bottom, which indicates the disease quite clearly. Just to sum up, or to have some take-home messages, we present a new method that is able to detect a various large set of diverse anomalies. So unlike before, we're not just focusing on hyperintensities, we do really a diverse set of anomalies. And by this, we managed to reduce the bias in what we can detect. So we're not detecting only hyperintense lesions, and we also not bound to detect something that we introduce in the training, like a coarse noise level. Of course, looking forward, we need these data sets where you can actually evaluate these methods better. So we have diverse anomalies with pixel-wise localizations, or even bounding boxes would be enough in order to drive the field forward and have some kind of a benchmark for the new methods that are developed, and not just look at hyperintensity, since there might be more than that. Thank you I will answer some questions now, but for further discussions, please stop by the poster. And if you had a really good eye for detail in the talk, you would notice that there are still some hallucinations in the pseudo-healthy versions. If you're wondering how you can improve that, you can check our latest work for that.
Thank you. We have time for questions.
A very nice talk. So I just have a very naive question. So in medical imaging, it's a common practice. We remove the skull before we do the analysis. So can you comment a little bit whether your learning performance will change if we, remove the skull?
Yeah, thanks for the question. The skull might have some randomness in it. So if you remove it, it might be easier for some methods to learn the tissue distribution. Especially, I think any random feature, it's difficult to capture in a latent dimensionality, right? So even the cortical foldings, they're quite unique, so it's difficult to map to a latent manifold and then recover from it. That's why I also have these slight hallucinations in the reconstructions, and there are ways to improve it. So just to answer the question, if you remove the skull, probably you'd get a bit improvement in some of the methods, since you don't have this hyper-intense skull around the brain. It wouldn't change dramatically.
Thank you.
Hey, thank you for the talk. So have you looked at adversarial attacks for perturbing the input images such that your autoencoder actually cannot detect the out of distribution?
Very good questions. We didn't, but this would be really a good test to see how well we really constrain the healthy distribution, or what we think it's the healthy distribution. Would be a good test to test the boundaries, since even the small pathologies were kind of clear in our set, so we can really differentiate between healthy and small pathologies. But of course, the question is like, where is the boundary? What cannot we detect? And this is a good question for future work. So thanks a lot.
Hi, thanks for your great talk. I have a question. How do you think it would work on more variable anatomies in the brain, like mammography, for example?
Sorry, the question?
Yeah, if you've tried it with other anatomies in the brain, and how it would work.
So is it a question how well we capture the variability in the brain?
Yeah, if you can like make the difference between variation as natural and variation like anomaly.
Well, this is the biggest challenge. So you put really the right question. You have a large variability in the normal distribution in medical imaging as compared to a computer vision, where you have one object which stays there all the time and it's looking the same. For instance, industrial inspection. So that's the challenge of it, and that's also why most method fails, because you have this large variability. So you want to capture a lot of variability and details in the reconstruction, but you also want a really constrained reconstruction just on the healthy distribution. So this is a really tricky part. For that, you have to analyze the whole distribution and how well you can recognize kind of these variations. It's not straightforward. So I've been working on some bias project, and even if you train, for instance, on specific white female distribution, and then just change the demographics, it would be a great shift in demographics and would lead to even larger shifts in pathology. So this is a really area of research, how to capture all this variability. And I think you can do this just when you train on large populations. If you have these foundation models on UK Biobank, then you do really capture a lot of variability in the normality, and then you can do this analysis. On small data sets, it's quite difficult to do it, and it's probably also pointless.
So basically, we need enough data.
Yes, and proper validation.
And proper validation. Thank you very much.
If it's quick, one last question.
Hi, thanks for the talk. My question is regarding the initial set of data that you need to train this. So I assume you need a set of healthy data that is kind of the norm, and then from there you define what is out of distribution. Have you looked at, because in the real world you usually have troubles really finding, let's say at a clinic, a set of healthy data that is not compromised in some way. So have you looked at what the effect would be if you have compromised data, not fully healthy, but also some outliers already in the initial set? Have you looked at that as well?
Yeah, thanks for the good question. I didn't evaluate it, but I can, if you want, to give you my intuition of it. So usually there are different types of methods. These reconstruction-based methods are quite, I would say, robust to any variations or to subtle variations of healthy training set, since you kind of learn the distribution. So even if you have, also related to the previous question, some variability that's really out of the distribution, or it's really rare that you see this variability in the normal, it wouldn't capture it. So you would still get some false positives due to some really rare things that you even have in the training set. So for these reconstruction-based methods where you actually aim at learning this distribution, it's not a big problem if you have contaminated data sets. For other methods which actually use patches from the training, then of course it's more problematic. But I cannot give you like a precise quantification of this.
Thank you.
Let's thank the speaker again.
Right. The next speaker is Shahira Abosamra from Stony Brook University. The title is Unsupervised and Decomposition via Inversion Regularization for Multiplex Immunohistochemistry Images. Okay.
Hi, everyone. I'm Shahira Abosamra from Stony Brook University, and I'm excited to be here to present our work, Unsupervised Stain Decomposition via Inversion Regulation for Multiplex Immunohistochemistry Images. So first of all, what is multiplex imaging? Well, it's about simultaneously labeling multiple biomarkers in the same tissue section. So you can find and detect different types of cells, for instance, like find tumors, different immune cell types, and this will help you to then further analyze these, so you can get like population size, spatial colocalization, and this is very important for diagnostic pathology and cancer immunotherapy. This can be related to diagnostics and outcomes and so on. Now, most people who work with this kind of data, multiplex imaging, they use fluorescence data. And that's because it gives you the output like every stain in a separate channel. And that's very practical. However, it is very expensive. Another type of multiplex imaging is bright field microscopy. So it's inexpensive, it is cost-effective, accessible, the microscopes are accessible, and it doesn't require expensive software or visualization tools. However, the catch is, the result is like a single image, RGB image, with all the stains mixed together like you see here, on the left. So you see like the different types of cells at the bottom, and they are all together in one RGB image. And if you want to use this data, you need to first separate this into different channels. You need to create some kind of segmentation map of the stains like you see on the right. So the existing methods, they do not work well when you do this. Like there are some methods for mixing these kind of multiplex stains, but they do not work very well when you have more than like 4 biomarkers. So if we want to make this practical, we need some unsupervised approaches that can scale with increased multiplexing. And this is what this paper is about. So to present our method, we need to first present the concept of stain concentration maps. So say we have this set of reference stains, and we have a concentration map for each stain. So like, for instance, it's very clear for the first one, that's the brown. It's the same brown region that you see in the image. And if you multiply each vector by its concentration map, this will give you a stain color map. Adding them up, you can get a reconstruction of the image. And in this formulation, you need to take care also to add a background stain. So this is like a dummy kind of staining. It doesn't really exist, but it's important to get a correct reconstruction. Now, if you want to put this in mathematical form, this will be like the stain matrix multiplied by the concentration map to give you the pixels or the image. And this is a law in physics called the Beer-Lambert law. It represents a linear representation, or a linear relationship between the stains and the concentration maps. However, this is only valid in the optical density space. It's not true in the RGB space. So that's optical density measures the absorbance of light as it passes through a medium. And it's the negative log of the RGB, so it's easy to get that. Now, this is the formulation that most unmixing methods use. So you have the stains, you have the image, and you want to optimize for the concentration maps. And if you have if the number of stains in the S vector, the S matrix is less than or equal to 3, then you can have a closed form solution. However, when the number of stains is greater, there is no closed form solution. The system of equations is underdetermined, and you need to find another way to optimize this. So previous methods, they tried to use some kind of regularization, like L1, to get some good sparse solution. However, it does not work well when you go beyond like 4 biomarkers. And so in this work, we try to overcome this. We train a deep learning model, and we train it with a novel inversion regulation, which allows us to scale with increased multiplexing. So what is the inversion regulation? Okay. This is what we saw before. We have the image, we have on the top the stains, and the concentration maps, together we can reconstruct the image. Now, the inversion regulation, we get an inverted version of the stains, or the complement of the stains. So if a stain is RGB, then its complement or inverse would be 1 minus R, 1 minus G, 1 minus B. And together with the same set of concentration maps, we try to reconstruct the inverted or complement image. So the inversion regulation, in a nutshell, it tries to enforce that the concentration maps work well for both the image and its inverse. And to see this, this is the model that we have. So we have its convolutional autoencoder, where the input is the stains and the image, and the output are the concentration maps. To train it, we reconstruct the image from the predicted concentration maps and apply a reconstruction loss. But like we said, this is not enough to get a good solution. So we also use the same concentration maps with the inverted stains to reconstruct the inverted image and apply another reconstruction loss for the inverse image. It's very simple, and it is very effective, like you see here in this image. So if you look, it's maybe difficult for you, but yeah, it's very pretty good reconstruction, or like a stain segmentation. And to see okay, so this seems like a trick. Why does it work, right? Well, like we said, the inversion regulation, it promotes solutions that satisfy both the image and its inverse. And this kind of choice was not random. It all comes down to the properties of an effective regulator. What do we want from a regulator? We want there to be a solution that satisfies both the original input and the regulation. And it wants that regulator to add constraints that will eliminate suboptimal solutions and promote desired sparse solutions. And to see how the inversion regulation helps, this is basically about the special relationship between a color and its inverse or complement. When an object absorbs light of a particular color, we perceive it as the complement or inverse color, and vice versa. And quantitatively, in the HSL space, a color and its inverse have the same saturation. And the color and its inverse have contrasting luminosity. So first, the same saturation. Saturation is correlated with the amount of pigment present. In other words, the concentration. So we can conclude that there is a solution concentration maps that would satisfy an image and its inverse. And that's the first property that we want. Second, the contrasting luminosity. We can show that luminosity is inversely proportional or correlated with absorbance. And, and from there, so a color and its inverse would have also contrasting absorbance. This will allow us to eliminate a large portion of the undesired solution space. And we can see this with a very simple example here. If we consider the tissue color, for instance, the white color in the tissue, right? It has high luminosity, it has low absorbance, and so it has low optical density. So in the Beer-Lambert law, you can just add the white color to any pixel, and it would not have any effect in the resulting reconstruction. But if you look at the inverse, that would be like a kind of blackish color, and it will have high optical density, and so it will greatly change any pixel it is added to, and it will not give us a valid reconstruction. So there are other examples in the paper how this is actually very helpful, but this is in a nutshell how it, to give you an intuition, how it is able to eliminate many undesired solutions. And this is, another qualitative result. And so to evaluate this, we have a set of images like the ones which you saw, and we have dot annotations, like for each cell. The pathologist would annotate the cell with the class, the biomarker there, and we use that to compute an F-score. So we compare two unsupervised methods, and our result, like in the last row, they are superior to all these unsupervised approaches. And we also compare to weakly supervised methods, and our result is comes second best after the best weakly supervised approach, the color AE. And this is comparative qualitative results. So we have here the second column, that's the dot annotations, but converted into superpixels for visualization. And next to it is our result. And we see how it looks very close to the superpixel labels and to the color AE, the supervised methods next to it. If you look at the last three columns, the unsupervised methods, they are very messy and make a lot of mistakes. So yes, conclusion or in summary, we have proposed a novel method for unsupervised stain unmixing in bright field microscopy, where we can scale to a larger number of stains. Like here we had 7 or 8 biomarkers multiplexed together. And our solution, Inverse AE, is a convolution autoencoder that decomposes the image into stain concentration maps. And to ensure that the resulting concentration maps actually reflect the dominant stain at each location, we use a novel inverse regulation loss. Our method, Inverse AE, as you saw, it makes bright field microscopy not just a cost-effective, accessible solution, but it also makes it practical. And in the future, we would like to also consider, like here, we were considering that every location has one dominant stain that we were segmenting. So we want to also extend this to model co-staining. Yeah, thank you so much. And please come to our poster and any questions?
Yeah, open for questions.
Hi. Thank you very much. That was a very interesting talk. I was wondering if your method is agnostic to the type of marker you're staining, because I know that different colors are sometimes used for different markers, like it's independent. So would it transfer if now, I don't know, the CD8 is not red, but maybe blue?
Yes, it's agnostic to that. It doesn't care. So it's just the different colors. So it doesn't know that CD8 is purple, or it's here it was actually purple. But we tested this on other data sets where we had a complete different set of staining, and it worked well as well.
Okay, cool. And have you any intuition about how much the scanning profile and the staining variation impacts the success of the stain separation?
Can you repeat the question? Sorry.
Like we've just seen that if you use different scanning profiles, you get quite a different variation in the intensity of the colors, for example, also between the images, like depending how old the block is that you use to cut, for examples. Like, have you tested a bit how big the impact is of that, or
no, not really, but I imagine that it should not be that much variation that would affect the result. That's my imagination. And you have the part where you input the stain vector. So that's so what we do there is that we ask pathologists to just collect in the beginning regions, like marked regions that are very good at showing the pigment that they want or the staining that they want. So I guess if you can use just a different set, if it's very much a different set of staining, looks very different, then maybe that can help. But in general, I don't think it would be a big issue.
Okay, thank you so much.
Yeah. Sure.
Okay, limited by time, so let's thank the speaker again. Okay, the next speaker is Zhang Xinbian. The title is DRIMET, Differentiation for 3D Incompressible Motion Estimation in Tagged MRI.
Yes, thank you, Chair, for the kind introduction. And hello, everyone. My name is Zhang Xing from Johns Hopkins. I'm a second-year PhD student, and I'm very honored to be here to present our work, DRIMET. It stands for Deep Registration for 3D Incompressible Motion Estimation in Tagged MRI. So a little bit background in the MR tagging. So it's a special MR imaging technique that will magnetize the tissue with a spatially modulated pattern. So when the tissue moves, the tags will move along, so that we can track the motion of the soft tissue. And it has a wide application. For example, decades ago, people use it to track the motion of the cardiac, and also people track the motion of the tongue to study the speech and swallowing functionality. And also people track brain motion to study the traumatic injuries. And in this work, we are particularly interested in tongue. According to American Cancer Society, a lot of people with oral cancer have troubles in swallowing or speaking or even sleeping because their tongues are affected. And from the technical perspective, we think it has a few very interesting points from the engineering perspective. So it moves relatively quick relative to the temporal resolution of the scan. And the motion is aperiodic, so it's different from the heartbeat, from the cardiac motion. And also the tongue is highly deformable during speech because it has a lot of very delicate muscle groups. So in this work, our goal is to track the 3D tongue motion through the image registration framework. So we expect it to be fast and accurate, but also the estimated motion should also be biologically plausible. So by that, I mean it needs to be both diffeomorphic and incompressible. So diffeomorphic, given the transformation field, diffeomorphic means that we can find an invertible transformation. So when we compose those, we end up identity transformation. And also for incompressible, we know the water is incompressible, and a lot of tissue, human tissue like brain, heart, or tongue, which consists of the most part of the water, can also be assumed to be incompressible. So there is one important feature that is the Jacobian determinant of the transformation field is unit everywhere, and we will use that feature later. So since we framed this tracking problem in a registration framework, so there are a lot of registration algorithms out there that people may familiar of. For example, the C method from the ANT toolbox, or the iLog daemons, and its extension version called pvira. And those are traditional approaches, and they usually have good accuracy and can achieve diffeomorphic or even incompressible motion estimation, but they usually suffer from the low speed. And more recently, the deep learning registration approach like voxelmorph can achieve very high speed during the inference time and achieve a relatively good performance or even much better performance. But it has trouble in finding the incompressible flow, or at least a missing feature. So we're thinking, so can we do it better? And this is the overview of our method. So take two tagged images at two different time points, and we send it to a pre-processing pipeline and also a deep learning registration method to find our motion phi. So let's first get into the pre-processing part. So with the tagged images, and you'll see there are 3 volumes because we put 3 orientation tags. Because we want to find the 3D motion, we need 3 orientation tags to solve the aperture problem. And the first thing we do is to interpolate or to upsample the image volume to isotropic 3D grid because it has poor through-plane resolution. And then we use an algorithm called HARP. It stands for harmonic phase, which has been widely used in processing tagged MRI data. So the benefit of HARP is it can be run very fast, and it's robust to the tag fading. And tag fading is one tricky thing that we do. That's the reason we do not directly register the raw tagged images in registration. Instead, we like the harmonic phase because it's a materials property, which means it will move with the tissue. Then we can take, or the traditional approach will take this harmonic phase image as a proxy in the registration to find the motion. But again, there is a tricky thing called phase interpolation. We know if we want to train a deep learning-based registration algorithm, we need to interpolate the image. And the interpolation, that operation itself needs to be differentiable, like a bilinear interpolation. However, different from interpolated intensity image, phase is kind of a tricky thing because if you want to find the, for example, the value at y0, you need to do, first you need to unwrap the phase image and then do the interpolation. So this unwrapping phase is not quite differentiable. So think of the solution is quite simple actually. It's called sinusoidal transformation. We simply take the phase value and apply the sine and cosine function to generate two corresponding images. So each phase value corresponds to a sine cosine pair. And then we turn this discontinuity in the phase to a continuous pattern. And previously we need unwrap the phase to do interpolation, but now we can directly do the interpolation, for example, bilinear interpolation, and this becomes a differentiable module that is very important in training the registration network. So this is the overall pipeline. So by far we have covered the preprocessing part. And from the preprocessing, we will get 3 sine cosine pairs for fixed and 3 for the moving. And we will concatenate those channel-wisely, send it to a neural network to predict the motion. And that's all it takes during the inference time. But in order to train the network, we need to warp the image. We need to warp the moving image by the deformation field to create a warped image and try to minimize the discrepancy between fixed and warped moving image by minimizing similarity loss. So here we just use MSE as a similarity loss. And also on the deformation field, people will usually apply some regularization to make it smoother, to make it look more realistic. And here we want to focus on this incompressibility loss. So in order to learn this incompressibility, recall that it has a great feature. The Jacobian determinant is unit everywhere. So the general idea is to push it to the push the Jacobian to the unit. It's very straightforward. And here are some details. So we first compute the Jacobian determinant of the transformation field phi at location x. And then we apply a logarithm over the determinant to symmetrically penalize the expansion or contraction. And then we apply, because we use a logarithm, so we use something like a ReLU function to eliminate the negative determinants. And we don't want to apply, and we only want to apply this constraint in our tongue tissue or heart tissue instead of the air gap in oral cavity or the blood. So this first term will push the determinant to unit, and the second term is just to prevent all the determinants from being negative, because in the first term we use a ReLU to ignore the negatives. So the overall training objective is just the 3 objectives combined. So here are some details on data we use. So we have 25 tag MRI data, and each case has 26 time frames, and people will speak a thing, a shell, a souk repeatedly until the acquisition finished. Interestingly, we have 2 patients that has undergone glossectomy, which are considered as a pathological case. So part of their tongue are removed in the surgery due to the cancer, and those cases are only preserved for testing. So here are some qualitative results. And this shows a 3D model of the tongue. There's tongue tip, tongue dorsal, and the root of tongue. So it's usually larger than people would think of the size of tongue. So in this case, we have a fixed image, which is taken when subjects speak us, so the tongue is in the neutral position. And the moving image is when the subject speaks in, so the tongue will move backward and downward. And we compare with this iLog or extension called Pivira, which is famous for its ability to estimate incompressible motion. And we find this, our approach can better align the taglines, and also from the determinants, our determinants are closer to unit, which implies a more incompressible motion estimation. So quantitatively, we also find our approach have a faster speed, which is very important in practice, but with also better accuracy, incompressibility, and the diffeomorphism. And the ablation on the incompressibility loss also shows efficiency. And we also explore the performance when we increase the time gap between the two registered frames. And we see all the method performance degrades, but ours degrades less. And also this, we evaluate on those two pathological cases, and note that our model are only trained with healthy controls. So we can achieve relatively well good generalizability to those pathological cases. Even in the training, we have never seen that. So in conclusion, we propose an unsupervised deep learning motion estimation method on the tag MRI data with two key components. So one is sinusoidal transformation to enable the differentiability, and another is an objective function for learning an incompressible flow. So the take-home message is this can be run fast, and the estimation are accurate, it's 3D dense, and incompressible. But there are some limitations in future work. So you may notice current framework only take a pair of frames, but the nature of tag MRI is sequential images. So can we incorporate more temporal information in the framework? And also the face and tag images have periodic patterns. So what if the periodicity in the image meets a large motion? Can the unsupervised registration algorithm solve that ambiguity? Yeah, that's the future work. So in the end, I want to thank all the members at ICL, at Hopkins, and also our collaborator at Harvard and MGH and Maryland. And the code is available, and welcome to my poster at M08 for further discussion. Thank you.
Time for maybe a question? I'll ask one that may be kind of quick. With your approach, you have three terms in your loss function. Mm-hmm. Could you elaborate a little bit on how you went about optimizing those hyperparameters and maybe discuss how sensitive they were?
Yeah, that's a good question. So currently, we just use a grid search algorithm to find the best hyperparameters. But later on, we tend to use something called hypermorph. Some people might heard of that to find the best hyperparameters. And we find, so the smoothness penalty doesn't really cause it isn't very sensitive, but the incompressibility loss kind of a little bit sensitive. But we don't have run any quantitative analysis on that point. Yeah. Yeah, please.
Well, thanks for the talk. I have one question about your transformation. So basically, you're applying a sinusoidal transformation to your face image. was just wondering, have you tried face unwrapping as a technique to apply that to your training data?
Yeah, that's a good question. So we did try the global face unwrapping before, but the thing is, I tried a deep learning based and algorithm, and it was trained on synthetic data set. So to train that face unwrapping, it usually requires a synthetic simulated data set. However, when I apply this synthetic trained model into our real data set, there are probably some domain gap that it doesn't really perform well. Yeah, because in like tongue imaging, there are a lot of air gap in the oral cavity, and yeah, the face unwrapping doesn't do very well once it encounters those noisy parts. Yeah.
Okay, thank you. So there, I'm not sure if you're familiar, but there are traditional algorithms for face unwrapping. There are quite a number of them. So if you're curious, but I'm just wondering, because your sinusoidal transformation is basically introducing local minima in your registration, because every time you wrap the sinusoidal transformation, you have basically a local minimum in your cost function. So I was just wondering if your transformation is robust, or if your registration is robust to that, to large shifts, or whether you have to rely on small time or small steps between your time steps.
Yes.
All right, thank you.
Yeah, thank you.
Let's thank the speaker again. That'll close the session. If there are no other announcements, then we'll start the poster session. Thank you.
Thank you. It used to be a good balance. I saw the original is through pathology.
doing it? Great. I don't have to do it. If Deepak's doing it, I will just take a seat. Okay. Yeah.
Including the questions. Sometimes they can go a little bit more or less. Because the goal is just to give 15 each. Good. Oh, that's good. We have this. Who was not there this morning.
Sounds good.
Cool. Yeah, we have the first one. Do you want to introduce the session, or do you want me to do? Or?
You can do
Okay,
it.
okay, okay. Your name Sohail.
Yes.
I never know how to pronounce something.
No worries. That's fine. Completely understand. So we introduce ourselves. You introduce the session, and then we introduce ourselves.
All right, cool. Well, I guess we can start. Slowly people are coming in and so on after the poster session and coffee break. So we're starting with the first actually graph-based method session. And we have a series of 3 talks. By the way, if the authors or the presenter could maybe be close to the stage. So we can start with the first one. The first one on T-cell graphs by Linda Studer.
We're good? Okay. Hello, everybody. My name is Linda Studer, and welcome to my presentation on tumor budding T-cell grafts assessing the need for resection in PT1 colorectal cancers. Now, let me start with a little bit of background on PT1 colorectal cancer. So the T is the T from the T and M staging that you might be familiar with. And the T1 stage is actually the earliest local stage, so it has a minimal invasion depth just in the 2 inner layers of the colon. And pathologists make recommendations for treatment strategies decided based on the polyps that are usually removed during a colonoscopy. And they look at 4 different factors. So this is based on the Swiss guidelines, but I think the European and US ones are very similar, if not exactly the same. And so they look at the tumor grade, they look at the infiltration depth of the tumor, they look at the presence of lymphovascular invasion within the polyp, and very recently they also look at the tumor budding score. And then based on these factors, the treatment strategy that is recommended is either watch and wait, which is basically do nothing and just get continuous follow-up colonoscopies. And the other one would be to undergo surgical resection of the colon, which is a very extensive surgery where 20 centimeters or more of the colon get removed. So it's quite an invasive surgery. And what we actually see from literature is that 70 to 80% of the patients do undergo resection. That is because if one of these risk factors is present, then automatically a patient is considered high risk. So the guidelines are actually very cautious. But when we then look at a surrogate marker for prognosis, which is lymph node metastasis, we can see that of these 70 to 80 patients that undergo resection, 90% of them are actually lymph node negative, meaning that they would have a very good prognosis and probably would have been all right without the resection of the colon. And as a consequence, we think, it's been suggested in multiple papers that we most likely have an overtreatment of these PT1 early stage cancer patients. And of course, there's a myriad of problems that comes with that, such as, for example, I think the most important is clinical complications from the surgery. And since screening programs are getting more and more common for colon cancer, we're also catching more and more of these early stage patients. So this patient group is growing, and it's really we could really have a high impact if we find a better way to assess high-risk patients which would need the resection versus those who do not. Now, the idea behind this work is that we wanted to focus on 2 well-known established prognostic biomarkers in colorectal cancer. One of them is actually tumor budding that I've mentioned before that's been recently added as a risk factor. And tumor buds are cells of 1 to 4, are clusters of 1 to 4 cells that are spreading out from the tumor, detaching. They're also hypothesized to be linked to metastasis. And this is kind of we can think of this as the attack of the tumor against the body. And then, of course, we have the immune system that is coming in as the defense. So this has been described in papers as the attacker-defender model. And the big defenders that have been shown to be the very important ones are the cytotoxic T cells, also known as T killer cells or CD8 positive cells. So we really wanted to look at these cells because it's also been shown previously that if we look at them in combination, it's actually a better indicator for survival and other features in multi-stage cohorts. And so we really wanted to take this a step further by not only doing scoring, but kind of mapping out their interaction in the tumor microenvironment and building a graph representation. And graph representations are also, in my opinion, a very nice way to condense information over a larger region while also being able to inject some domain knowledge. So here it would be 2 prognostic biomarkers. And we you can here see an example of how tumor buds can look like on an immunohistochemistry slide. And the T cells are the ones in red. So, and we want to use this graph-based approach to see if we can do a better risk stratification. Now, of course, we collected a data set for a PT1 cohort, And this is a retrospective cohort, so we know the treatment strategy that these patients had, and they either underwent, so the majority underwent resection, where we know their lymph node status, and then the few ones that underwent the watch and wait strategy, we have a follow-up where we know whether or not they had a recurrence of cancer. And so according to this information, we have regrouped them into a high and low risk group, where the lowest groups are the ones that did not have any lymph node metastasis, or if they're from the watch and wait group, they did not have a recurrence of cancer. And all the other ones we consider as high risk, and as anticipated, this group is much smaller, so we also have an imbalanced data set. And we have a bit more slides than patients, because for some of the patients, multiple slides were collected. And we're using double immunohistochemistry stained slides to identify our tumor buds and T cells, where you can see, again, examples from the previous slide. Now, let me walk you through our experimental evaluation framework. So, of course, in the first step, we need to build our graph representations. And then, based on the graph representations, in the second step, we can do a graph classification, which we do using a graph neural network. And then as an output, based on the softmax, we get an indication for either high or low risk. Now let's talk a bit more about the graph creation. So we have our scanned whole slide images, where my colleague John Mellebokhorst from Radboud UMC has performed automated tumor bud and T cell detection with algorithms that they have developed there at their lab. And so you can see in pink and green, we have the detected objects of interest. And then in parallel, Heather Dawson, my pathologist that I work with, has annotated the tumor budding hotspots according to the international standards, because really for a first try, we wanted to focus on a region that we knew was going to be biologically interesting and prognostically relevant. And then, of course, we create the graphs. Now, how exactly did we do that? So, as I already mentioned, for the nodes, we have the T cells and tumor buds. And then we also defined a set of node labels, the first one being the node type, so tumor bud or T cell. Then the second one being the coordinates centered to the center of the hotspot. And then the third one being an image-based descriptor, where you use an ImageNet pre-trained transformer to create, just like to use the output, the embedding vector as a feature for the nodes. And then for the edges, we have defined 3 different edge insertion functions that I'll show you in a second. And for edge label, if it's used by the graph neural network, depends a bit on what kind of setup you have. We use the distance in micrometers. Now we have, since we didn't really know what the graph representation would be, we decided to come up with 3 different ones to compare. So the first one is the Delaunay triangulation, which is very commonly used for cell graphs and has been long shown to be a very good graph representation in histopathology. So of course we also use that one. And then after discussions with the pathologists, we have defined 2 more. So the first one is kind of inspired by the Delaunay representation, where we Delaunay triangulate the tumor buds and the T cells are connected to any tumor bud within a radius of 100 micrometer, kind of trying to like zone in onto a potential biological interaction like area around the tumor buds. And then the third one is more based on fully connected graphs, where we fully connect the tumor buds, and then the T cells we connect to their closest tumor bud with a cutoff of 100 micrometers again. And then around a tumor bud, we fully connect all of the T cells. So we kind of have these like 2 levels of fully connected graphs. This is why we call it the hierarchical representation. Okay, now that we have our graphs, we can move on to the actual classification using a graph neural network. And we use a network with 4 convolutional layers. And then in the end, you get the output as high and low risk. Now, let me go into a bit more detail on the graph convolution. So in the first phase, is what we call the message passing phase, is when we do the aggregation of the information of the local neighborhood, where information of the node features is sent to all the neighboring nodes. And then we have a message aggregation function and the message that comes in, and then some update function. And together, this is called usually the message passing functions. And I have compared the performance of 3 that are very commonly used, again, in the literature and have shown to be good. So GraphSage, GIN, and GATV2. And then as you stack multiple layers of the graph convolution, you can get information from like a larger and larger neighborhood in the graph. So as we want to do a graph level classification, we need to get a graph level feature vector. And this is what is created during what is usually known as the readout phase. And so we use the global ad pooling to create a single feature vector where we just like sum up over all of the node feature vectors within the graph. Then we also test whether jumping knowledge can be helpful, which has been also shown to be in some cases helpful, which is where we don't only consider the output, the graph after the final layer of convolution, but actually from every single step of the convolutional layers. And then we also tested whether or not adding some of the pathological information that we have, thanks to the reader study, could be important or could be helpful for the MLP header. So yeah, let me show you a very condensed table of the results. As you can imagine, I have tested out many different configurations. So if you want to look at all of them, please look at the paper. It has a very long appendix. And so as a baseline to compare against, we used the criteria set forth by the Swiss Society of Gastroenterologists, which is based on these 4 factors that I've talked to you about in the introduction. So I had my pathologist Heather to go through the cases and like score them based on that, and then we compare it to our definition of the high-low risk groups, and we can see that we get about 22% of true negative rates. So this is the recall for the low risk group. So again, like it's not surprising that we've seen this in literature that we have quite a high overtreatment, most likely. And we really also want to keep a high recall for the high-risk group because we really don't want to miss any of these patients. So the true negative and the true positive rates were the 2 metrics that I focused on most in this work as for the evaluation. And we can see that actually with a very simple graph representation, so just using the type as a node feature and the Delaunay triangulation as the edge configuration, we can already decrease the overtreatment by 10% by increasing the true negative rate to above 31%. And I was really happy to see that because for me, I always feel like the simple solution is the best, probably in terms of generalization. But I also saw that if we make things a bit more complex, so we add more node features and we move on to like this, the graph representations that I defined, we can actually even bump this to over 40%. But these results are the results over a 5-fold cross-validation, by the way. So yeah, what did we find? So our key findings is that we are able to decrease overtreatment without the loss of sensitivity by up to 20% compared to the guidelines. We saw that simple graph representation is already working really well. And we also found that all of the best performing systems, well, I would say unsurprisingly, were using the histopathological data for the classification header. And I really would like to validate this on an external PT1 cohort, especially to see which of the graph representations actually does generalize the best. And I'm currently also working on applying these ideas to a stage 2 colorectal cancer data set. Now, I would like to thank all of my co-authors, Andreas Fischer from the universities in Fribourg, who's my PhD supervisor, then my colleagues John Malabokhorst and Iris Nachtigall from Nijmegen from the Radboud UMC, who helped me with some of the technical things, and Iris with the collection of the data set. Then my pathologist, Heather Dawson, who was always there for me for all the medical questions. And last but not least, Inti Slobek and the whole Odyssey Digital Pathology team in Bern. So thank you very much for your attention. I'm very happy to have any question. And if my poster session is sadly already over, but feel free to come up to me for discussions. And you can read the paper here with this link. Thank you so much.
Excellent. Yeah, thanks for sticking with time as well. So questions? Any questions? Microphones?
Yeah, nice presentation. I have a question about the feature vector for each node in the graph. So since you have already used some prior knowledge like the tumor bud or the T cell, so have you think about add some prior knowledge to the feature vector beyond the ImageNet or the VIT feature beyond that? Have you thought about add like cell density, those kind of like a manual feature to the vector?
Yeah. So the M-bending vector is one of the features that I tried, and then the coordinates is another one. But we found that this was not very informative, which again to me wasn't that surprising. But it's commonly used, so I thought I'd give it a shot. And then the node type. But yeah, definitely like something that's sometimes also added is like the connectivity, so the number of outgoing edges, I think, and then yeah, there's or like even the angles like of the edges to the other cells. There's definitely more options to do here in terms of like domain knowledge features other than the node. I think maybe if we would add descriptions of the cells, like maybe the number of the cells in the tumor bud, or even something about the nucleus, because that can be quite informative in the cancer, that could definitely also be options, or the size. I think there that the challenge might be a bit to have it like homogeneous between, because you need the same features for the tumor buds and the T cells, and they might not be like the same interesting features. So I think that is something that would need to be a bit balanced, like weighed against each other. Yeah, thank you.
Hi, thank you. Very nice presentation.
Thank you.
So I was wondering, because for graph convolutions, they've sort of been shown to, well, at least as far as my knowledge goes, they seem to sort of top out by an X number of layers, which is relatively low still. How do you think that relates to your choice of architecture for your graph?
Very interesting question. Yeah, unfortunately, I don't know how many of you are working in like graph neural networks. It's not like we know that a U networks well and you can just throw that at it. It's still very heuristic and very frustrating. So yeah, I think my colleague Anna has tried with her larger graphs to add more layers, because if you have a larger graph, maybe more layers is better, but it was not very successful, unfortunately. So I think there's still a big discussion in the community, like why exactly this is not so good. And so I tried to stick with something that was like recommended. Usually it's recommended between like 3 and 5 layers, so I really kind of wanted to stick there. I've also done some experiments, but normally it doesn't really help much, to be honest. And yeah, from what I've seen from her work, even if you have very large graphs, it doesn't seem to add much either. So I can only, like, my speculation might be that you have kind of like a dilution of the information once you get too far. But yeah, I'm sorry, I don't think I have a finite answer for you on that.
No, that's fine. But it seemed to be that the hierarchical one was doing very nicely, and then I guess it kind of makes sense that you're quickly going to like...
Yeah, I also wanted to try, just didn't have, like, I didn't come around to it, to dare do like kind of like, because some people do also kind of these like hierarchical graphs almost, in this case as well, if we would have like a local readout and then get a feature vector for the tumor bud and then do like another readout, because I know there's some really nice work by Guillaume Jean where they use like cell level and tissue level graphs that they combine and to kind of like update one feature vector using the other one. So yeah, I think, as I said, this was kind of like a first try in this direction. So I think there's plenty of room for optimization and for like more ideas to try out. Yeah, thank you.
Thank you very much.
Cool. One last question, maybe Brahms. Yeah.
Hi, thank you. Do you have an idea of the reliability of the reference standard?
As in the baseline, you mean?
No, of your data set?
Oh, my data set. Well, so the histopathological data I know is very good because it was created during a reader study where I think 5 or even more pathologists participated, so there I'm very confident. When it comes to the graphs, it is of course sensitive to the quality of the automated detection algorithms. We have done an evaluation there, so John Mellas recently published his paper and he's shown that he has a very good...
No, but it is about having lymph node metastasis, right?
Oh, you mean
Low
that? Yeah.
risk,
So
high
okay.
Risk. Did they sample all the lymph nodes? If they
yes,
would have
exactly.
Done
So when the colon is resected, I mean, I'm not a pathologist, but from what I understand is when they take out the colon, they take out all of the adjacent lymph nodes and they scan every single one of them because this is important for the staging. Because even if one is present, we have like N+ or N1 stage. So I am confident that if the surgeons are doing their job really well, which I think they do, we have a good picture of the lymph node metastasis situation.
Well, I'm not so confident. I know that they can have to look up to 90 slides. It's very,
yes,
from what we know from the literature, it's very easy to have disagreement among pathologists.
Yes, but I think, like I have a colleague who has done like automated detection of lymph node metastasis. So I think from what I remember, he has found, I mean, it's not perfect, but I think it was, yeah, I would have to talk to the pathologist again, honestly. But since there are so many involved, I have a good feeling. Thank you.
Cool. Thanks to the speaker. Yeah.
Okay, so I believe that actually we forgot to introduce ourselves. I'm Sohail Kalouri. I'm an assistant professor in the computer science department at Vanderbilt University.
And I'm Hervé. I'm in Montreal. Yep.
Yes. Okay, so our next speaker is, our next talk is going to be on a geometric deep learning framework for generation of virtual left ventricles as graphs. And the speaker is going to be Sude Akalai.
Hi everyone, my name is Sude and I'm doing my last year of PhD in University of Leeds, United Kingdom. I'm a member of a SysDeep group directed by Professor Alex Frangi. The topic of my presentation today is about a geometric deep learning framework for generation of virtual left ventricle as a graph. If I want to talk about some introduction here, first of all, I would like to mention the importance of shape generation. Basically, generative shape statistical models has a wide range of application in modeling of anatomical shapes, including identifying disease, predicting them, or generating virtual population for computer simulation. In silico clinical materials or digital twins are a prime example of this application that can significantly benefit from the virtual data. Basically, in silico clinical materials bring the possibility of gaining valuable information for new therapies or medical devices. However, building a rich and descriptive generative model is a challenging task. This is because the actual world or real world data derived from the real world image data set related to the different individuals do not generally share the same topological structures. And existing methods cannot generate coherent and anatomically plausible population of data, and most of them cannot capture characteristics, features in each individuals. So the topic of our research, that it's about targeting this idea that we can address the problem of shape matching, establishing correspondence across the data, and basically generating data. So we came up with the idea of presenting an unsupervised probabilistic deep generative models for anatomical shape. This is a framework that is applicable to the surface mesh data with varying topological structure and with the absence of correspondence. When I say there is no topological structure, I can say in the same word that the number of vertices or the number of points in its shape is different. Sorry. So this framework leverages from presenting shape as a graph, because with presenting shape as a graph, the model can leverage from learning geometric features via the nodes, and also it also can learn the surface features via the edges. And it incorporates geometric deep learning like graph convolutional neural network. So here is the framework that we present. We call it attention-based shape matching generation framework. So the data that we started to work is 3D image data, but we extracted the surface mesh data from this 3D image data as a pre-processing. So the whole data set that we have as a training data is a surface mesh data with different number of nodes or different cardinality. So this hierarchical geometric deep learning framework is basically embedded in two sections. The first section is about establishing vertex-wise correspondence across the training data, and it's followed by nonlinear generation networks. In the first section, basically the model can can present an unsupervised learning-based correspondence procedure, which is based on graph convolutional neural network and attention mechanism. Basically, this part of the framework can derive the vertex-wise correspondence across the training data by measuring the similarity between the nodal embeddings. I should mention that in this part, we used a spatial graph convolutional neural network. Basically, it can aggregate the local features using some attention mechanism to extract the nodal embeddings for each graph or each shapes. And after that, we follow the framework with domain transformation, which means by extracting or establishing the correspondence map, we are able to transfer all the data in the training data set to a template domain. And this template shape is also optimized during the process, and the model is able to generate a population-derived atlas model. After finding all the data or warping all the data set on a template domain, so we can just address the problem of existing methods, generation methods, and pass all the warp data to the nonlinear generation network, which we consider it as a beta variational autoencoder. It allows the model to capture all the nonlinearity or all the variation in the shapes. And with discovering the disentangled latent representation of shapes, the model is able to generate realistic synthetic data at the end. Here is a probabilistic graphical model for ASMG network that we present. It basically shows the hierarchical representation of the model and all the dependency across the framework. As an input, we consider node features, as you can see, as a matrix of X and adjacency matrix of K. Both are indexed by K, which means the topology of each training data is different. In a higher level, we are able to extract or derive the latent variables, which allows us to establish the correspondence C, and after that, we warp all the data, and we are able to generate synthetic data in a beta VAE. In terms of experiments and results, I should mention that in this paper, we demonstrated our framework with LV data extracted from the UK Biobank dataset. The number of training data was 1K, but I should mention that the framework that we presented is generic, and it's applicable to the other type of anatomical data. As you can see, some results in our supplementary materials of the paper. And the baseline model that we compare our model with this is the model based on the rigid registration and PCA, coupling these two models. We evaluated our model in two sections, shape matching quality and generation network. I should mention that in the part of shape matching procedure, we consider refinement strategy to make sure that all the data warped to the template domain are realistic. So if you want to I'm sorry about the notation. So if you can see, this is a schematic of shape matching procedure. This is basically, that's why represented in the previous slides. You can see how the shape matching procedure can find the similarity between two nodal embeddings and present this probabilistic correspondence map between two shapes. So here is some visualization and quantification of shape correspondence. Basically, in this figure, the blue line shows the meaningful correspondence between some selected pink landmarks, important landmarks on LV, and if you can see here, the color-coded points actually quantify the value of correspondence, which is basically the posterior probability of meaningful connection between two vertices or 2 points. In terms of quantifying the warp shape in a template domain, you can see some results here which compare our methodology with registration-based shape matching. So as you can see, the blue shapes present shapes in actual domain, in actual cardinality, and the gray shapes actually present the data after transformation. So we aim to, we basically are looking for the model that can preserve more details and do not, we would like the model to not lose any information, which is basically comes with the realistic correspondence map that the model could generate. In terms of the actual quality of the domain transformation using the shape matching procedure, we also consider two Hausdorff distance and chamfer distance, and we compare our result with registration-based shape matching, and we consider our method with refinement and without refinement. As you can see, the result with our methodology with refinement comes with lower minimum errors. And also it has the lower standard variation, which shows the robustness of the model. And these two panel basically shows how much the model can preserve more detail and how much the model can improve the performance of correspondence mapping when we use the refinement strategy, because we would like the testing points to go further to the green gradient section. In terms of generation quality, we consider two matrices of generalization and specificity, because for generating virtual population, we aim to present enough variability of actual population while the synthetic data will remain plausible. So basically, the higher performance model is the one that has lower distance metrics in generalization and also has lower distance metrics in specificity. So as you can see, our model has higher performance. In terms of clinical relevance, we consider the volume of generated shapes and we compare it with the actual population. So this is basically shows the percentage of synthetic data related to the actual population within the confidence interval of the different confident intervals of actual population. As you can see, again, the SMG model has the higher acceptance rate. And here is some of the synthetic data that the model could generate. As you can see, the model could generate different variation because we use the nonlinear variational autoencoder when it compares with some sort of linear generation methodology, it can preserve more details and can preserve more variation of the shapes. And also the model some example shows that the model could generate realistic shapes. If I want to conclude the talk, I can say that we present a non-supervised probabilistic deep generative model, which is capable of generating virtual left ventricle cohorts. And it can resemble the actual data set with different cardinality. So we use the surface mesh representation of shapes instead of using the 3D dimension representation of data. I mean, instead of using the voxel grid data set, which is really highly sparse and memory intensive. We used a spatial-based graph convolutional neural network, which allows us to handle irregularity across the training data. And the model has higher performance in compared with other methodology because it shows the higher degree of variability and plausibility. So it is applicable to the in silico clinical materials, and it's possible to use it in conducting digital twins. And this was part of my PhD research, and as an extension, we worked on joint clustering shape matching generative network. And yes, thank you, everyone.
So
I'm happy to.
We have time for one question. Okay, so if, I can ask a question. You jointly solve the matching and the generation, right?
Yes.
So as a baseline, there are a lot of, registration-based approaches that you can use for solving this matching. Have you looked at some of the classic approaches for finding matching as opposed to using the attention-based?
Yes, as
method?
I mentioned, the baseline model that I used was a registration-based methodology. But the point is, as you know, all of them use the point cloud-based representation of shape. It's not a learning-based methodology. And most of them lost some information when we use it as a like shape matching procedure. So, but our model is basically is a learning-based methodology. So it can, in comparison with like registration-based shape matching, we use the similarity-based learning, but the other methods like registration, they can only work on local area and find it based on the local distances. So our methodology is more accurate in finding correspondence. This is based on the result that we obtain. And also, it's more generalized. We show it in different type of topology. For example, in liver data set that we have more variety of morphological variation. We showed that registration-based method cannot work perfectly. So.
Okay. Thank you. Let's thank our speaker again.
Thank you.
Now we have the last talk of the session with the vessel former, like transformers but for vessels, with Chimney Prabhakar. And I'm sorry if I mispronounced the name.
Superson is actually the presenter.
Hi everyone, thank you. Chinmay was supposed to give the talk, but unfortunately he's not here because of visa issue. So I'm Shupro, who will be speaking here. So it's a joint work with Technical University Munich and University of Zurich, with co-authors Johannes, Ivan, Rajat, Bran, Florian, and our supervisor Björn. So the problem of graph extractions from images is ubiquitous in many medical imaging applications
and preclinical research. The idea is that we want to extract the nodes. The nodes here means the bifurcation points between the vessels, or a curvature of significant angles. And the edges between the nodes are actually the vessels. So this is particularly of interest for radius features, especially which is important to do fluid flow simulations or labeling the particular blood vessel segments. And this is usually done in traditional approach to first do a segmentation, followed by skeleton extraction, and then pruning of the skeleton to have a compact graph representation and some feature extraction on top of that. And to this end, we asked this research question, can you do this end-to-end from image to the graph with relevant graph features? So we propose an architecture termed vessel former, which takes an image in 3D volume of an image as an input, followed by feature extraction through a CNN backbone, which goes through a transformer encoder for contextualized image features. And then at the decoder, we have learnable object tokens and relation tokens, which interacts with the image features through cross-attention. And the refined tokens goes through head, which gives us the particular location of the nodes and the connection between them in terms of edges. So edge features, edge is really important to connect these nodes, but this is a similarity score between the nodes, and it cannot capture a span of the vessels as such. And also, it limits to quantify the physical quantity of the radius. So for this purpose, we introduce an additional token specifically for the radius informations, which in combination of two object token goes through an additional regression head to predict the radius information. And this gives us the architecture to jointly predict the nodes, edges, and the edge properties, which marginally increase on the network complexity where we started from. Altogether, we kind of combine all predictions from 4 heads, which gives us the final output. And this network is end-to-end trained with 2 classification laws on the node and edge classification, and the node location regression and the radius regression laws. And this kind of predicts the edge and edge attributes jointly. So we benchmark our architecture on a synthetic vessel datasets where the ground truth information is known. Because in this dataset, the graph is generated first and then converted into an voxel representations. And where you observe that our proposed architecture performs the graph extractions at the same time doing radius information, and which does not deteriorate if we do not use this edge information, edge attribute information, and just the graph structure predictions. And on top of that, the radius information that you have is on the sub-pixel accuracy, which is really kind of promising for our future approach. Qualitatively, you can see that the extracted graph closely agree with the ground truth graph as color-coded with the heat maps as radius features. So this is our architecture, which produces the edges and the radius jointly. However, we are still doing this information in the patch level, and in the application we have to do it in the whole 3D voxel space. So for this, we asked the second research questions: how can we extract a non-overlapping patches from a 3D volumes, apply our method, have these subgraphs, and how can we combine these subgraphs to get the full graph in the end? One can apply an approach to find the pairwise distance computation. However, we'll soon run into a combinatorial complexity because it kind of grows to the n factorial or n combination of 2 approach. So this is the second research question we asked: can you have a more efficient approach to merge these non-overlapping subgraphs into a full 3D subgraphs? So for that, we propose an algorithm, which I'll try to explain in a pictorial sense. So first, we identify that non-overlapping patches could be divided into 8 subfields, as shown in 8 different colors, so that in any junction points, there is no same colors of patches together. So this kind of makes the node merging algorithm parallel, run could be in parallel. We can just select any 2 pair of subfields and does our operation in parallel. And secondly, we kind of identify that this computation of node proximity is better handled if we embed these our subgraphs into 3D space and just compute their voxel pace overlap in the IU in the form of intersection over union. For that, to compute a meaningful intersection over union, we resort to a gray dilation of the node locations so that we allow a node into one subregions to kind of inflate a bit and kind of go beyond these other subregions and vice versa. And then we kind of compute the intersection over union. And if it goes beyond a certain threshold, we just merge these two node locations into our new node locations. We compute the same matrix on this volume level, which kind of shows that it kind of performs on par with the standard voting architecture, voting method, which is a traditional approach, and kind of produces kind of scalable algorithm for merging different sub-patches. Qualitatively, you can see that it kind of produces reliable prediction in a complex network graph in the volume level. However, there is also failure cases. This is one example where these long ranges of vessels are kind of discontinued. So in summary, we propose an architecture to jointly predict node, edge, and edge attributes, and propose a scalable algorithm to merge together. But there is a room for future work, which is the first one is to kind of apply these on a real data set. And the challenge for the real data set application is to find the ground truth first, or the reference to kind of have a proper fair comparisons. And also future directions to incorporate different constraints such as flow to kind of prevent those failure cases in the local level would be of interest. So to this end, I conclude this presentation, and please feel free to ask questions.
Cool, we have time for questions, yeah? There's 2 microphones, and I'll make the awkward silence so people can...
That was a great talk, thank you. Correct me if I'm wrong, but when you do this vessel merger, so only you grow the dilation from the 8 corners of the chunk, I guess. So would you expect there be other vessels from the faces of the chunks, like disconnected vessels?
By corner, you mean the corner of the volume?
Yeah.
No, actually, we are doing we let the subfield region dilate in all the vessel nodes. So it doesn't really depend where the nodes is, where the corner on the boundary of the patches. So it kind of grows independent of where the nodes actually. So it kind of takes those situations into account as well.
Okay. It grows until it finds another node, right?
Yep.
Thanks.
Maybe one more question? Cool. In that case, we can thank the speaker.
Thank you.
So at this point, we're going to transition to several more teaser talks. So these are the flash talks or the lightning round talks. And this will be for tomorrow's posters, for tomorrow's short paper posters. So if you are on that email, you should be up front, please, so we can go through this quickly. And then I will have announcements about dinner afterward. So please stay for all of them, because I have important information about food. And also for science, but also for food. So first up, we actually have a poster from today that was unable to present at their assigned slot for their flash talk. So we'll have P212 back up. So thank you.
Hi everyone, I'm Divyam. I'm a PhD student at NYU. This is joint work with Daniel Sodikson, Kyungin Cho, and Sumit. The motivation of our work is that often in medical imaging, we don't know that what conditions you would encounter in testing. You could have patients from different demographics, you could have different machines, you could have different scanners, like there could be just infinite many possibilities on how evaluation could change. the takeaway is that don't use batch norm if you're expected to have a distribution shift during testing. The reason being that in batch norm, the statistics captured during training are also used for testing. So if you're having a shift, those statistics basically do not generalize to your testing distribution. We propose that you should use group norm or layer norm, which are good alternatives and can give you performance boost of as good as 15%. We tested for MRI for classification, but we hope that our results will generalize across different tasks, including segmentation detection and also across different modalities. So yeah, thank you.
The next speaker is not here, so we'll go to S018.
Hi, everyone. My name is Yehan. I'll be doing a poster tomorrow on afternoon. I'll be talking about a new label augmentation method using dilation and erosion method. So we came up with this method because we cannot use data augmentation in radiograph images because it has a strict pattern and recognition. And if we do any augmentation, it will make the image invalid. So we came up with a label augmentation method to using dilation and erosion. If you see the second image, you can see that it dilates and erodes as it goes. So it shows a good result on small data set using only 163 trained data set, and it is showing a 1 degree absolute mean difference in angles. So you can also implement these on diverse areas. So please come see me tomorrow, and I'll be waiting for you guys on T36. Thank you.
Okay. Our next speaker is S022.
Hello, everyone. I'm Hao Chengdai, and we are going to present our work, neural operated learning for ultrasound tomography inversion. And ultrasound CT has been an emerging image modality that in breast imaging and can produce quantitative images with less costly machines and also free of radiation. However, the conventional full-wave inversion method is computational expensive and also memory burdensome. And in our work, we apply the neural operator for the first time to convert learn the mapping from speed of sound to from the time of flight to the speed of sound. And the operator learns the nonlinear mapping offline and then predicts the speed of sound field with a single forward pass. And the neural operators demonstrate the superior accuracy and also very well generation abilities. And feel free to come our booth T37, and we're more than happy to answer any questions about our work. Thank you.
All right, thank you. And now we have S025.
Hello, everyone. This is Rajat Sones from Merck Research. So this project is actually a part of the safety assessment process, which is usually done on any drug candidate. We analyze if the drug is safe for consumption. So one of the safety assessment process is done on the reproductive and toxicology study. In the non-clinical phase, we test these drugs on pregnant rabbits and see if it causes any kind of abnormality in the fetal growth. So we are trying to automate this process using deep learning, but you have the usual challenges about annotations, the quality and the quantity, and then these bones are sometimes not well calcified, so it's tougher than a typical segmentation problem. So come talk to me to learn more about the safety assessment process and how we moved from a limited suboptimal annotations to annotating a larger set and then using that in deep learning, and also managing smaller bones, a segmentation of smaller bones using unit models. I'm looking forward to it. Thank you.
Thank you. And our next speaker is S031.
Yeah, hello, I'm Johann Engster from the Fraunhofer IMT in Germany.
And in our short paper, we investigated the WNet architecture for unsupervised segmentation of plugs in histological whole-slide images. So this architecture was proposed in 2017 and uses a reconstruction loss and a so-called soft and cut loss during the training. So in our experiments, we found out that the soft and cut loss of this WNet penalizes plugs in vicinity, and therefore we proposed 3 different weightings for this loss to overcome this problem. And in our results, we were able to show that we can, firstly, detect the plugs inside the whole slide images, and secondly, that the modifications were beneficial. Yeah, thanks.
Great. And next we have S035.
Hi everyone, I'm Anna Fry from the Odyssey group in Bern. Our project is about a gamma focus augmentation. So in histopathology, when we try to classify histologic elements, sometimes we need some context information. And so we have observed that by increasing the patch size around the object of interest, we might increase the classification performance. However, by doing this, the model might not be focusing anymore on the object of interest that we want to classify. And so we came up with this idea of using this gamma focus to increase the contrast in the center of the image where the object of interest is, and decrease the contrast in the surrounding to keep the important crop size, but force the model to focus on the region of interest, and by this keep the correct classification and also improve the classification performance. So please visit our poster T31 tomorrow and we can discuss further. Thank you very much.
And now we have S039.
Hi everyone, my name is Benjamin and I'm a postdoc at MIT. So here the problem that we're trying to address is, could we build equivariance in our models without having to learn it with data augmentation? And when I say equivariance, I mean translation and rotation equivariance. So equivariant networks, or ECNNs, are a first solution, but they don't generalize well, and they have a limited learning capacity because they only have a few trainable parameters. So here, we propose to increase their learning capacity by combining them with denoisers in a process that decouples intensity and spatial features. So our method is shown to outperform ECNNs and regular CNNs for rigid registration. Thank you.
And S067.
Hello, my name is Kaylin Winston. I'm a deep learning engineer at NVIDIA, and we did this research at the University of Washington. I'm actually presenting on behalf of Chloe Winston, who was supposed to be here today, but got stuck in Philly because of the bad weather. So our research is about applying self-supervised learning, specifically contrastive learning, to chest X-ray classification for pneumonia detection. And specifically, instead of using the classical methods of identifying pairs, similar and different pairs in contrastive learning, which uses methods like augmentations and transformations, we found that these don't work super well for medical images, and so we decided to try using radiomics features as a means for generating positive and negative pairs for chest X-ray pneumonia detection. And we found that 85% of the positive pairs that were generated using using nearest neighbor radiomics features had the same label, meaning they were both pneumonia or a control. And furthermore, 65% of the positive pairs had the same type of pneumonia, bacterial versus viral, which indicates that radiomics is a useful feature space for contrastive learning for pneumonia detection. And in our results, we found that we have around an 8% improved accuracy when doing this self-supervised contrastive pre-training step for pneumonia detection from chest X-rays. So come check out our poster tomorrow, and we'd love to see you there. Thank you.
And let's thank all the speakers once more. Thank you. Yeah. Okay, so for some important information. Now we're going to go and clean up posters, and you'll have some downtime. buses will start meeting or taking people from outside of this building at the red statue or red art piece featured in the picture, which is exactly outside of the doors, the front doors here. If you go out of this hall and turn right, that's where the buses will be meeting. And they'll start picking people up at 6 p.m. This is a reception, so there'll be hors d'oeuvres and bowl stations, which are essentially small meal stations. It's not a sit-down dinner, but unless you're bulking or otherwise really, really hungry, there should be enough food that it will be a great meal. But it's not a formal meal, it's a reception where we'll be walking around a wonderful museum. And if you see a bus leaving, don't panic, we're not leaving you behind. There will be multiple buses and they'll be in a loop. However, we strongly recommend that everybody get on a bus to the reception or some other transport, some other transport by 6:40. So we'll continue looping, but yeah, hopefully everybody will be on their way by that point. The last bus back is 10 p.m. If you want to stay, that's not a problem. You don't have to tell anybody, or if you decide to wander off, you're all adults. But the last bus back here is 10 p.m. from the venue. If you have additional questions, feel free to ask one of the organizers, and otherwise, we'll see you on the bus.